the universe breathes outward in a steady drift that astronomers call the Hubble expansion, a pattern in which distant galaxies recede from one another, not because they travel through space, but because space itself stretches. On the larger scales, the pattern is smooth and nearly uniform like ink marks on a rubber sheet, pulled evenly in every direction so that each mark moves away from every other in direct proportion to distance. This proportionality sets a clean baseline for motion, the quiet metronome beneath the changing sky. Against this baseline, every galaxy also carries a smaller separate motion that does not follow the uniform stretch. That additional motion is called a peculiar velocity. It points toward or away from nearby concentrations of matter or sideways along the filaments that thread the cosmos, and it gives each galaxy a slight personal drift superposed on the general expansion. The two kinds of motion coexist at once. The background expansion dominates at very large separations and grows with distance, while local gravitational tugs shape the smaller offsets that matter most to structure. To make sense of this two-part dance, the observer adopts a map that expands with the universe, a comoving grid whose rulers stretch as space stretches. In that comoving view, the broad flow recedes into the background and the deviations become the story. Matter is not spread evenly. Gravity gathers it into an intricate web of long filaments, broad sheets and dense knots, and it leaves between them wide hollows called voids. Along a filament, a galaxy tends to slide toward higher density, while within a void it tends to drift outward toward the surrounding walls. On the larger scales, the web itself changes only slowly, so the peculiar flow lines drawn on that comoving map trace gentle curves toward concentrations of mass and away from underdense regions, because motion must be measured with respect to something. Careful reference frames anchor this picture. One anchor is statistical. Take the average of many galaxies over an immense region, so that small local swirls cancel and define rest with respect to that average. Another anchor is physical and universal, the faint microwave glow left from the hot early universe. If an observer is truly at rest with respect to that ancient light, the glow appears the same in every direction. If the observer drifts one side of the sky looks slightly warmer, and the opposite side slightly cooler, that simple two-lobe pattern fixes a direction and a speed for bulk motion. With these anchors, the expansion becomes a well-defined background, and the peculiar field stands out as a map of gravitational response. The rate of expansion sets the tempo of the background drift. It is described by a quantity that changes slowly as the universe ages. Early on, the mass of matter slows the expansion. Later, a property of space that astronomers call dark energy makes the expansion accelerate. At the scales relevant to galaxy neighborhoods, gravity still sculpts the local field, yet the background stretch persists quietly under everything. A galaxy may recede at many thousands of kilometers per second because of the expansion, while also carrying a few hundred kilometers per second of peculiar motion toward a denser region. The difference matters for interpretation. To read the peculiar field, one must know true distances, not just speeds, because the background recession and the local drift blend together in the shift of spectral lines. Distances are the hard half of the task. They come from a ladder of methods whose rungs are tied together geometric parallax nearby, repeatably bright variable stars farther out, explosive events whose peak brightness can be standardized at still greater ranges, and other carefully calibrated indicators. Each rung brings its own uncertainties that must be traced into the final flow map. Single galaxy distances scatter, so surveys collect large samples and average across many objects to reduce noise and reveal the common vector. In the resulting maps, a crucial signature is coherence. Over distances of many tens of millions of light years, the peculiar velocities do not point in random directions. They align across wide swathes of space, as if countless small creeks sense the shape of a broad valley and begin to run the same way. Such coherence signals gravity from structures that extend across large volumes, rather than from a single bright object. The analogy to water stops there. There is no friction in the cosmic flow, no drag that bleeds away speed in a medium. The velocities arise and change only under the pull of gravity, and they persist over long times, unless a new gradient in mass redirects them. Because gravity responds to all mass, not only to what shines, the peculiar field is a direct probe of the unseen. Most mass in the universe is dark matter, a component that does not emit or absorb light, but outweighs ordinary matter by a wide margin. It forms halos that overlap and merge, and it defines the backbone of the web. Luminous galaxies trace that backbone imperfectly, like lanterns hung on an invisible scaffold. When a flow bends, it often follows the gravity of a dark structure with only a faint luminous signal. In this way, the velocity field acts as a cartographer that can outline weight, rather than light mapping the true gravitating landscape in which galaxies move. The expansion might suggest a universal tendency for everything to separate from everything else forever, but bound systems resist the stretch. A cluster keeps its galaxies, a galaxy keeps its stars, and a planetary system keeps its planets. The expansion acts between such bound islands and not within them. This separation of scales ensures that the background drift does not dilute gravitationally bound structures or confuse the measurement of their internal motions. It also clarifies the task of the flow analyst, who regards each island as intact and asks how those islands move with respect to one another under the pull of the larger web. Time enters the picture with its own vast scale. The characteristic periods for these motions span many billions of years. A human lifetime samples a tiny segment of a typical curve in the flow. For that reason, the study of large-scale motion relies on wide surveys that provide instantaneous snapshots across enormous volumes. Those snapshots are then compared with models that evolve the field under gravity and expansion to test whether the observed pattern can grow naturally from plausible beginnings. The agreement between model and map builds confidence that the flow is read correctly, and that the inferred mass distribution is faithful to reality. In this outer frame, the purpose is definition and calibration. The expansion supplies the universal rhythm. The peculiar velocities supply the local melody. Reference frames tied to the ancient microwave glow and to broad galaxy averages keep the score consistent. Distance ladders set the scale. Coherence across wide regions signals extended weight. The absence of friction lets those signals endure without being blurred away. Dark matter underlies the pattern, and ordinary matter marks it with light. With the baseline established, every subsequent step inward can be taken with a clear sense of what belongs to the background stretch and what belongs to the gravitating structures that guide the smaller drifts. The map is now ready to be read as a field of motion rather than a collection of isolated objects, a continuum of gentle currents flowing across the larger scales that nature allows, and within that continuum each galaxy, including our own, carries a modest but telling offset that encodes the pull of its surroundings without yet naming any particular source. The large-scale structure of matter appears as a web when mapped in 3 dimensions, but a web alone is only a pattern of density. Motion gives the pattern direction, and turns a static picture into a field with sources and sinks. In that field, a useful concept emerges from fluid thinking without borrowing its mechanics. One can define basins of attraction regions within which the velocity vectors of galaxies point toward a common convergence. Each basin is not a rigid object with an edge fixed in space. It is a domain outlined by the orientation of many small arrows, the peculiar velocities that express the gravitational response to an uneven distribution of mass. Where arrows bend toward a shared center, a basin is present. Where they fan away, a watershed boundary is near. On very large scales, these basins fill space like gentle valleys, separated by broad saddles, and they evolve only slowly as structure grows. In this framework, a supercluster is not just a crowded knot of galaxies. It is a flow domain whose extent is traced by the way galaxies move. Traditional supercluster lists group luminous systems by proximity and count, but such lists can blur true dynamical ties. A flow-based definition asks a different question. If a galaxy were to drift along under the existing gravitational field, and with no collisions or shocks to disrupt it, would it continue to move toward the same general convergence as its neighbours, or would it peel away toward another? The answer partitions space into basins that reveal how gravity organises motion across hundreds of millions of light years. Within this language, the basin that contains the Milky Way has been delineated by large reconstructions of the velocity field that combine distance measurements with models of gravitational flow. The name given to this basin is Laniakea. The word is a label, but the concept rests on the mapping of vectors. Starting far from the local details and moving inward, the field shows that galaxies in a broad swath of the nearby universe stream toward a common region rather than in random orientations. The boundary of that domain is where flow lines turn away and feed neighbouring basins that lead elsewhere. The line is not sharp. It is a surface that meanders through space set, where competing gravitational influences balance, and where the direction of motion flips from one convergence to another. Out at the periphery of this domain, the motion is gentle and the arrows are long, reflecting the dominance of the background expansion. As one steps inward, the peculiar component grows. The sizes involved are vast. The diameter of the basin spans on the order of several 100 million light-years. Inside that expanse lie familiar named structures such as clusters and walls, but the basin is defined by motion, not by catalogue entries. The mapping process that identifies it proceeds by careful accumulation of galaxy distances, and by an inversion of the flow that asks what distribution of mass, both luminous and dark, is consistent with the observed velocities. The result is a map in which streamlines run like contours of intent through the cosmic web, crossing sheets sliding along filaments and skirting voids. The Milky Way sits within this basin, not at its centre, but within one of its interior corridors, a position tied to the local group and its neighbours along a filament that feeds inward. The local group is a small island of two large spirals, the Milky Way and Andromeda, accompanied by smaller companions. As a bound system, it ignores the background stretch in its internal structure, but as a whole it participates in the larger flow. Its peculiar velocity vector points in a direction that aligns with many nearby galaxies over great distances, confirming its membership in the same basin of attraction. That alignment is one of the key signatures of the basin's reality. Where many independent objects share a trend of motion, a common gravitational descent is present. The map of Laniakea also shows what it excludes. Beyond the basin boundary, the vectors turn toward different convergences associated with other concentrations of mass. Those neighbouring basins are not disconnected islands. They touch across wide saddle regions where the gravitational pull of one domain fades and the influence of another grows. The border is a dynamical divide drawn by the present configuration of mass and sustained by the slow change of the web. Tracing inward across the outer edge of the basin, the field leads through filaments that host groups and clusters, then down toward a central region, where many streamlines terminate. Termination does not mean a physical surface or an end to motion. It indicates that the peculiar component aims consistently toward a deep gravitational minimum embedded in the larger web. Within the basin, the flows are not turbulent. They are coherent over long stretches, and their curvature registers the cumulative tugs of dark matter halos and luminous assemblies superposed. This coherence is strongest when volume averages are taken over many tens of millions of light-years, because small-scale noise from local interactions cancels, and the large-scale intent stands out. The reconstruction that yields Laniakea is iterative. Distances carry uncertainties, and the inversion from velocities to mass distribution must be regularized to avoid imposing noise as structure. By comparing the derived flow with independent traces such as galaxy density and cluster catalogues in multiple wavelengths, the map is refined. Where dust or stellar foregrounds complicate the view in optical light radio and infrared surveys, add missing entries so that the vectors remain anchored across the sky. The emerging picture is not a perfect portrait, but a consistent field whose main features persist under changes in method and sample. That robustness is a practical test. A real basin must appear under varied assumptions and with different subsets of data. In this test, the domain that includes the Milky Way remains coherent, and its boundary remains recognizable even as details shift. Within the basin, the role of voids becomes apparent. Voids are not empty, but they are underdense. Their lower gravity causes the surrounding matter to respond more to distant attractions, and the flow inside a void tends to drift outward toward the encircling filaments and sheets. These outward drifts contribute to the clarity of the basin's inward trends, because they feed galaxies onto the structural rails that guide them toward the central convergence. The map thus contains two complementary motions. From underdense interiors, matter slides out and onto walls and filaments. Along those structures, it moves inward toward higher density regions that lie deeper in the basin. The Milky Way follows this general scheme, carried by its filamentary context toward the shared interior, without leaving the bounds of the domain that the vector field defines. On scales smaller than the basin, the field can be decomposed into contributions from nearer and farther mass concentrations. That decomposition is a bookkeeping exercise rather than a shift of concept. It shows that the inward trends seen at large scale are built from many overlapping pools, some relatively close, and some much more distant, all summed into the single direction of the peculiar velocity at any given point. The basin model does not require a single central object acting alone. It requires only that the superposed gravity of the mass within the domain be sufficient to orient the flow lines toward a common destination. Because most of that mass is dark matter, the luminous map is an incomplete guide, and the velocity field is the more faithful tracer of the true distribution of weight. The usefulness of the basin framework is practical as well as descriptive. It converts a complex sky filled with thousands of discrete systems into a continuous field problem with clear boundaries and internal coherence. It aligns with the way gravity acts over large volumes, and it provides a neutral language for comparing observations with simulations that evolve matter and motion together. In that language, Laniakea is the outer region to hold in view as the path moves inward. It is the gravitational catchment of which the Milky Way is a part, a domain mapped not by lines on a photograph, but by the orientation of countless tiny arrows inferred from spectra and distances. With the domain located and its boundaries sketched by motion rather than by brightness, the next inward step can remain within this same basin, following the flow along its interior structures toward the region, where many of its streamlines converge with the understanding that the frame is now fixed and the scale is set by the basin itself, rather than by an arbitrary catalogue of neighbouring systems. To turn a sky of scattered lights into a map of hidden weight, astronomers begin with two measurements for as many galaxies as possible: how fast each one appears to move along the line of sight, and how far away it truly is. The shift of spectral lines supplies the first. When space stretches, distant galaxies show their atomic fingerprints nudged to longer wavelengths, and the amount of that shift yields a recession speed. Yet a shifted spectrum blends two causes at once: the smooth expansion that grows with distance, and the smaller drift imposed by nearby gravity. Distances supply the second ingredient needed to separate these parts. Only by knowing how far a galaxy sits can one subtract the expected expansion at that range and isolate the residual motion that points toward mass. Distances are assembled on a ladder whose rungs overlap so that each can be tied to the next. For the very nearest galaxies, geometric parallax fixes scale from simple triangles as Earth moves around the Sun. Farther out, standardizable candles appear sources whose true luminosity can be inferred from a measurable trait. Certain variable stars brighten and fade with a period that tracks their intrinsic brightness. Once that relation is calibrated nearby, it carries farther. Explosive transients can also be standardized through the shape of their light curves, pushing the ladder deeper into space. Additional rungs measure the texture of unresolved stars in large galaxies, the abrupt onset of helium burning at the tip of the red giant branch, or empirical ties between how fast a spiral rotates and how bright it is, and between the structural properties of elliptical galaxies and their luminosity. Each method brings scatter and systematics. The strength lies in overlap. Where two rungs meet, cross-calibration trims bias and propagates a common scale. With distances in hand, the logic is straightforward. For each galaxy, the expected contribution from the smooth expansion is computed at its distance using the adopted background model. That expected value is removed from the observed line of sight speed to yield a peculiar velocity. By itself, a single peculiar velocity is a noisy clue. In a field built from thousands of such clues across the sky, patterns emerge. Coherence is the key diagnostic. Over many tens of millions of light years, the residuals should not aim in random directions if gravity is organizing motion. Instead, they tend to align into broad streams that skirt voids, slide along filaments, and bend toward dense regions. The map grows from those alignments. Observations directly provide only the radial component of each motion, since transverse drifts are far too small to track at cosmological distances. The three-dimensional flow is therefore inferred statistically. One family of reconstructions assumes that on large scales the flow is irrotational as expected, when gravitational instability gently amplifies small initial fluctuations in an expanding background. Under that assumption, a scalar velocity potential exists, and the observed radial components can be integrated to recover the full vector field after suitable smoothing. More general approaches cast the unknown density and velocity fields into a basis of modes and solve for their amplitudes using Bayesian inference. In those solutions, the data enter with uncertainties. Prior knowledge about the smoothness of large-scale structure constrains poorly measured regions, and the result is the most probable continuous field consistent with the catalogue. Techniques such as Wiener filtering naturally down-weight modes dominated by noise while preserving coherent features, supported by many neighbouring measurements. The step from velocity to mass requires a further physical tie. In linear theory, on large scales, mass conservation links the divergence of the peculiar velocity field to the underlying density contrast once the slow evolution of the growth rate with cosmic time is accounted for. In practice, this link is used cautiously. The field is smoothed over large volumes to stay within the regime where the approximation holds, and strongly non-linear regions such as the cores of clusters are treated with care or masked. The outcome is a three-dimensional grid that assigns to every location both a mean flow vector and an estimate of how much mass density deviates from the cosmic average. Reference frames must be handled consistently. A convenient standard is the frame in which the cosmic microwave background looks the same in all directions. Subtracting the dipole pattern caused by the motion of the observer shifts the entire catalogue into that universal rest frame so that a local drift does not contaminate the whole sky. Galaxies bound together inside the same group or cluster also require special treatment. Their internal orbits are not part of the large-scale flow. Analysts therefore replace such swarms of measurements with a single representative motion for the group as a whole to avoid counting internal speeds as bulk drift. Selection effects and biases can mimic coherent flow if left unchecked. Malmquist bias, in which more luminous objects are seen over larger volumes, and thus overrepresented at greater distances, can push average distance estimates low and manufacture an artificial infall toward the observer. Corrections include modelling the luminosity function of tracer galaxies using inverse correlations that reduce sensitivity to selection on brightness, and adopting volume-limited subsamples when the catalogue is dense enough. Zero-point drifts in any rung of the distance ladder ripple coherently through a whole subsample, so independent calibrations using separate instruments and separate techniques are prized. Redundant overlap between rungs allows the combined scale to be tightened and checked. Because the plane of the Milky Way hides large portions of the background sky behind dust, and crowding, a special effort is made to bridge the zone of avoidance. Radio surveys detect the emission from neutral hydrogen in spirals whose starlight is suppressed by dust yielding reliable recession speeds, and rotational widths for distance indicators that link rotation and luminosity. Infrared imaging pierces the dust to identify galaxies and measure their structures for use in distance relations that rely on surface brightness fluctuations or on the properties of old red giant stars. X-ray maps flag hot cluster atmospheres that anchor dense regions otherwise missed in optical catalogues. Combining these windows reduces the risk that the reconstructed field is twisted by a blind wedge on the sky. Independent traces of mass provide important cross-checks. Weak gravitational lensing measures the subtle shear that foreground mass imposes on the shapes of distant galaxies, offering a view of total matter that does not care whether it shines. Though challenging to apply on the largest nearby scales, lensing results where available can be compared with the reconstructed density field. X-ray observations of clusters reveal the depth of gravitational wells through the temperature and distribution of hot gas, adding another layer of consistency tests. Redshift surveys, which map the positions of hundreds of thousands of galaxies in 3 dimensions using spectral shifts alone, constrain how galaxies cluster, and the reconstructed mass field should predict similar large-scale clustering after a simple bias relation between galaxies and mass is applied. Simulations accompany every step, starting from initial conditions that match the statistical imprint of early density fluctuations. Numerical models evolve dark matter under gravity and expansion, and when feasible include gas physics for the luminous component. From these models, one can create mock catalogues that copy the selection functions, the sky coverage, the distance indicator scatters, and even the gaps imposed by the plane of the Milky Way. The same reconstruction algorithms are then run on the mock data. If the method recovers the known input fields within uncertainties, confidence grows that the same method applied to the real catalogue produces a faithful map. If the method stumbles under certain conditions, those regimes are flagged in the data analysis and treated with extra caution or excluded. The end product is not a photograph, but a field description. On a coarse grid spanning hundreds of millions of light-years, each cell carries a mean peculiar velocity and a density contrast with error bars. From this field, streamlines are drawn that indicate the path a test particle would follow if released at rest with respect to the expanding background. Where many such streamlines head toward the same region, when the field is smoothed on large scales, a convergence appears. That convergence defines a basin of attraction, in the dynamical sense a domain in which the present gravitational landscape guides motion toward a shared interior. Because most of the mass is dark matter, this dynamical definition is closer to the true gravitational geography than any map drawn purely from light. The picture that results is intentionally conservative. It emphasizes large scales where motions are coherent and where the simple connection between flow and mass remains valid. It averages over local interactions that would otherwise inject noise. It keeps careful track of systematic errors and uses independent data to test its main features. In this way, a catalogue of individual distances and velocities becomes a continuous 3-dimensional description of how matter moves and how mass is laid out. That description does not assign meaning beyond mechanics. It identifies where the field bends and how strongly it bends. It shows which directions carry matter in and which carry matter out. It prepares the ground for the next inward steps by providing a calibrated background against which particular structures can be weighed. Within this framework, the hidden mass that shapes the flow is no longer guessed from brightness alone. It is inferred from motion itself, and the map of the unseen is traced by the quiet sum of many small residuals pointing together toward gravity's deeper wells. Across the whole sky, a faint microwave glow arrives from every direction, with nearly the same brightness and temperature. This glow is the afterlight of the early universe stretched into long wavelengths by the expansion of space and preserved as a near-perfect background. Against that uniformity, one feature stands out even before any subtle ripples are measured. One side of the sky looks very slightly warmer, and the opposite side looks very slightly cooler by a comparable amount. This too-low pattern is called the dipole. Its origin is kinematic rather than primordial. It does not record sound waves from the young cosmos, or the imprint of ancient density contrasts. It records motion. If an observer moves through, the background radiation arriving from the forward direction is slightly compressed and appears warmer, while radiation from the backward direction is slightly stretched and appears cooler. The size of this warm-cool difference is set by the speed of the observer relative to the background and by the simple physics of Doppler shifts. Because the effect is proportional to speed, and because the microwave background is otherwise so uniform, the dipole provides a clean and robust way to measure bulk drift with respect to a universal reference. The path to this measurement begins on Earth, but the Earth does not sit still. It orbits the Sun at a speed of a few tens of kilometers per second, and that orbital motion alone would paint a small dipole across the microwave sky that cycles once each year as the direction of motion changes. The Sun also does not sit still. It travels around the centre of the Milky Way on a nearly circular path that takes hundreds of millions of years to complete adding another velocity component. The Milky Way as a whole, together with Andromeda and their smaller companions, moves within the local group, and the local group moves with respect to surrounding structures. To use the microwave background as a yardstick, one must sort these motions carefully and identify the net drift of the observer against that background. This sorting is done step by step. The annual contribution from the Earth's orbit has a known period and a known geometry. It is measured and removed. The small seasonal wiggle in the dipole amplitude and direction provides an internal check on instrument stability and calibration, because it repeats with predictable timing and size. After the orbital term is taken out, what remains is the steady dipole due to the longer-lived bulk motion of the solar system barycenter through space. Spacecraft that map the microwave background are designed to detect differences in temperature that are far smaller than a single degree. They sweep the sky many times, compare directions repeatedly, and carry independent channels and detectors to suppress instrumental drifts. The too-low pattern emerges strongly, many times larger than the subtler small-scale variations that later reveal the early universe's imprint. Its direction points toward a region on the sky in the general neighbourhood of the constellations near the plane of our galaxy, and its amplitude corresponds to a speed of a few hundred kilometers per second. This speed is not the orbital speed of the Sun around the Milky Way. It is the net motion of the solar system with respect to the frame in which the background looks the same in all directions. That frame is called the cosmic microwave background rest frame. Once this vector is measured, all other sky maps and catalogues can be shifted into that same frame by subtracting its effect. In practice, analysts transform the data into the CMB frame so that the dipole vanishes from the microwave map, and so that the reference for other measurements is globally defined. The dipole matters beyond microwave mapping. Any all-sky catalogue is subtly modulated by the observer's motion, because motion slightly brightens sources on the forward side, and slightly dims sources on the backward side, and because motion slightly alters apparent positions by aberration. The modulation is tiny, but across the whole sky is coherent, and it must be accounted for when comparing catalogues to the microwave background, or when stacking many objects to measure weak statistical signals. In the CMB frame, this systematic dip disappears by construction. The rest of the analysis can then proceed with a common zero point that does not depend on the peculiarities of the solar system's present path. The peculiar velocity of the local group is closely related to, but not identical with, the solar system's CMB dipole motion. The Sun orbits within the Milky Way, and the Milky Way and Andromeda orbit their shared centre of mass within the local group. By averaging over the motions of many local group members, and by modelling the internal orbits, one can infer the motion of the group as a bound unit, with respect to the microwave background. That group motion points in nearly the same general direction as the solar system dipole, and has a somewhat different speed because it excludes the solar and galactic orbital pieces. The alignment is expected if the local group is riding along a large-scale flow. The small differences between the solar galactic and group vectors are the bookkeeping adjustments that remove internal motions. Making those adjustments turns a local measurement into a clean tracer of bulk drift on scales beyond any single galaxy. The dipole is large compared with the delicate degree scale fluctuations that later power precise studies of cosmology. For that reason, the first step in analysing a microwave map is to remove the dipole both to shift into the universal rest frame and to reveal the smaller pattern beneath. The subtraction is not a matter of taste, it is a matter of frame choice. The primordial fluctuations that one aims to measure are imprinted in the rest frame of the early plasma that release the background light. The observer's motion overlays a smooth gradient that would otherwise dominate the map. Removing it exposes the true structure that records the physics of the young universe. A useful cross-check comes from the way motion also leaves a subtle fingerprint on the high-resolution pattern through aberration and modulation. The small anisotropies are slightly squeezed in the forward direction and slightly stretched in the backward direction, and their apparent amplitude is shifted by a tiny amount. These signatures can be measured and used to verify the speed inferred from the dipole itself, providing a consistency test that ties together different parts of the map. The strength of the dipole measurement lies in its simplicity and in its independence from local complexities. Dust in the Milky Way can redden and dim background galaxies in optical light and can hide structures entirely behind the plane. Gas can absorb radio lines. Foreground stars can crowd fields and confuse catalogues. The microwave background, however, fills the sky and has an extremely smooth spectrum close to that of an ideal thermal source. A two-lobe difference across the whole sky is not easily faked by local conditions. Instrument teams use multiple frequencies to separate galactic emissions and to isolate the pure background signal. They compare observations taken at different times of year to track the annual dipole, and to ensure that the measured steady dipole behaves as a true vector rather than as an artifact tied to the spacecraft orientation or to a particular part of the sky. The resulting velocity is therefore a secure anchor. It does not rely on any single cluster wall or filament. It defines a rest frame that is global. With this anchor established, galaxy flows can be discussed in absolute terms. A catalogue of galaxy distances and recession speeds can be corrected into the CMB frame, so that the smooth expansion is measured consistently in all directions. The residual peculiar velocities can then be compared with maps of mass and with reconstructions of the gravitational field. Large-scale coherence in those residuals gains significance because the 0 point is not drifting with the solar system's own motion. When a flow points toward a certain broad region of the sky, it does so relative to a universal baseline rather than relative to a local moving yardstick. In this way, the dipole enables a clean separation between what belongs to the expansion, what belongs to the observer's drift, and what belongs to the true gravitational response to structure. The direction of the measured dipole provides an intuitive picture. It points roughly toward the hemisphere that contains several prominent concentrations of mass at modest distances and away from the opposite hemisphere which looks into a region of less immediate weight. This does not mean that the microwave background itself is brighter because of those nearby structures. The background is global and distant. The alignment simply reflects that the local group and with it the solar system moves through space along a path influenced by the uneven distribution of mass in that general direction. The microwave dipole is the speedometer and compass for that bulk motion. Its magnitude sees how fast the frame moves. Its orientation says which way it goes. Because the expansion rate of the universe changes only slowly with time, and because the large-scale gravitational landscape evolves gradually, the CMB dipole will persist, with only gentle drift over human timescales. Its seasonal component due to the Earth's orbit will continue to provide a yearly calibration. Its steady component will continue to define the universal rest frame. As instruments improve and surveys deepen, the community returns to the same basic step of subtracting the dipole before exploring the finer structure beneath. That routine subtraction is a reminder that every map is made from a moving platform and that motion can be measured and removed cleanly when a universal reference exists. With the frame defined by the ancient light and the observer's motion carefully taken out, the analysis can move inward with confidence. The velocities assigned to galaxies now sit on a stable baseline. The residuals are tied to gravity rather than to the vantage point. The next scales to consider are those of our own small community, where the Milky Way and Andromeda share a drift through the nearby web. In that setting, the peculiar velocity becomes an immediate local vector within the same universal frame, and the flow lines that trace through the broader basin can be followed with the understanding that the 0 point is set by the oldest, most uniform light in the sky. Within the small archipelago of galaxies called the local group, the Milky Way and Andromeda stand as two dominant islands bound together by their shared gravity. A retinue of dwarf companions surrounds them, moving on elongated paths that record quiet tides from earlier passages. Inside this bound community, the expansion of space has no leverage. Orbits and streams respond to the enclosed mass, not to the universal stretch. Yet the local group as a whole does not sit still. It translates through the surrounding cosmic web with a peculiar velocity that adds to the background recession. That translation is the local expression of the large-scale flow, already mapped in wider surveys, reduced now to a single arrow attached to a small self-contained system. The internal picture begins with the Milky Way and Andromeda approaching along a nearly straight line that links their centres. The halos of dark matter reach far beyond their bright stellar disks, and across the space between them, those halos overlap and define a shared potential. The approach speed is of order a few hundred kilometers per second, and the separation is of order a few million light-years, both expressed with words, because the aim is description rather than bookkeeping. Around this pair, the dwarf satellites trace narrow planes, broad cones, and diffuse swarms, some on plunging paths that will feed the larger galaxies, and some on looping orbits that will persist for many orbits to come. These internal motions do not contradict the group's translation. They coexist on different scales, one binding the system the other, carrying it through the larger field. To measure the local group's drift, observers do not watch the group slide across the sky. The transverse drift is far too small for direct tracking on human timescales. Instead, they infer the motion by comparing distances and recession speeds for many galaxies spread across the nearby universe. For members of the group, they subtract internal motions that belong to orbits, such as the Sun's path around the Milky Way, and Andromeda's disk rotation. For galaxies beyond the group, they use distance indicators to separate the smooth expansion from the residual peculiar component. They then shift all measurements into the frame in which the cosmic microwave background appears the same in every direction. In that universal rest frame, the remaining pattern reveals the local group as a bound unit moving with a coherent velocity that points toward a particular region on the sky. The resulting vector is not owed to a single nearby mass acting alone. It reflects the sum of many contributions that add steadily over long times. In the general direction of travel lie familiar concentrations of matter at modest distances, including the Virgo cluster and the denser structures in Hydra and Centaurus. Beyond them, more distant weight adds a gentle pull layered through the background. In the opposite hemisphere, the path looks toward a region of lower density that offers less countervailing force. The net result is a gradual acceleration integrated into a steady speed aimed toward the denser side of the sky. This is not a fall toward a point, but a slide down a broad gradient set by the distribution of mass within the basin that contains the group. Dwarf galaxies add leverage to this inference. Those tightly bound to one of the two large spirals share the motion of their host when averaged over time, so their measured velocities help define the center of mass of the pair. Those nearer the boundary between bound and unbound regimes feel more directly the regional gradient from outside the group. Their distances and speeds, once corrected for internal orbits, trace the transition from internal dominance to external guidance. When the velocity field is smoothed over several million light-year streamlines thread through the local group, along the same general direction that guides nearby groups, confirming that the group is embedded in a coherent flow rather than isolated from it. Drift matters because it governs how the local group approaches its surroundings while preserving its internal structure. A group that moves along a filament experiences a slow change in the external gravitational field. Over very long times, those changes stretch or compress the outer orbits of satellites, and can align the preferred planes along which new companions fall in. The pattern of tidal debris around the Milky Way and Andromeda thus encodes not only the record of their mutual approach, but also the imprint of the larger web through which the group travels. Streams of stars crossing the halo mark former dwarfs, and the faint curvature of those streams remembers both the internal potential and the gentle shear imposed by the background field. A helpful way to connect scales is to imagine concentric spheres centered on the local group's center of mass. In the smallest sphere, only a few million light-years across internal motions dominate, and the velocity field is a tapestry of satellite orbits and the approach of the two great halos. Expand the sphere to a few tens of millions of light-years, and the internal tapestry blurs into a single arrow for the group, while the external field begins to bend trajectories toward nearby clusters and walls. Expand again to hundreds of millions of light-years, and the full basin of attraction emerges with broad streamlines that skirt voids, slide along filaments, and point toward a common convergence within the larger supercluster domain. The local group's arrow is the small-scale limit of those same lines. Turning the measurement into a secure number requires care with biases and gaps. The plane of the Milky Way hides a wide belt of background sky behind dust and star fields. Distance indicators carry scatter that can produce spurious flows if not modelled. Catalogues tend to favour brighter galaxies at greater distances, which can bias averages low and create an artificial inward trend. Analysts respond by using multiple independent distance methods, by selecting volume-limited subsamples when the data allow, and by grouping galaxies that share a common halo so that internal orbits do not masquerade as bulk drift. They also stitch the zone of avoidance with radio and infrared surveys that pierce dust and recover galaxies whose starlight is suppressed. In this way, the local group's vector becomes a product of many cross-checked inputs rather than a single fragile estimate. The language of attraction invites a correction. It can suggest a single source that pulls like a magnet. The gravitating landscape is not so discrete. Dark matter and ordinary matter fill space in an uneven way, and gravity responds to the total. Motion follows the gradient of that landscape. The local group is therefore not falling toward a solitary object. It is sliding down a gently sloped valley, carved by the superposed weight of halos and filaments, most of which are dark. The direction of motion aims toward a region where many streamlines converge. That region is extended not point-like, and its influence is felt long before its luminous content is fully mapped. The peculiar velocity is thus a cleaner tracer of the true distribution of mass than any catalogue built from light alone. The group's translation does not erase its internal future. The Milky Way and Andromeda continue to draw together on a timescale of several billion years, long enough that the surrounding field will also evolve. When they finally merge, the event will take place within the moving frame of the group's drift. Outer halo stars and satellites will feel the slow shear from the larger web, while the inner regions coalesce into a single, more massive system. Tidal streams will wrap into longer arcs that remember both the local encounter and the background translation, and new satellites arriving along the filament will add fresh strands to the pattern. As a kinematic quantity, the local group's peculiar velocity is modest compared with the recession speeds that the expansion imposes at very large distances, yet it is dynamically significant because it expresses the immediate response to the nearest layers of mass. Its direction and magnitude provide boundary conditions for any model that aims to reproduce the motions of nearby galaxies. Simulations that evolve matter forward from early conditions and that are selected to resemble the local environment can be compared with the measured vector. Agreement in both the group's arrow and in the arrangement of neighbouring structures strengthens confidence that the reconstructed regional field is faithful to reality. Set in this frame, the local group plays two roles at once. It is close enough that its distances can be established with geometric measurements or with well-calibrated standard candles, and its internal dynamics can be mapped with fine detail. It is also embedded in a flow that ties it to the wider basin, whose boundaries are drawn by motion rather than by light. The local group therefore anchors the narrative at humanly accessible scales, while pointing along the path inward toward named structures that contribute to its drift. The next of those in both distance and influence is the cluster that defines the nearest mid-scale weight on the route. With the local group's translation defined and its context clarified, the map can step inward without changing frames. The universal background remains subtracted by the ancient microwave light. The basin remains the outer boundary within which motion is interpreted. The group remains a cohesive island carried by a broad current. That current now guides the description toward the nearby cluster environment that adds a measurable component to the local group's arrow. In that next region, the same rules hold stay within the current scale, describe what the flow reveals, and treat gravity as the quiet shaper of paths through which the Milky Way and its neighbours drift toward their shared interior. The nearest concentration of cluster-scale mass along the local group's path is the Virgo cluster, a loose city of galaxies threaded through by hot gas and bound by a deep envelope of dark matter. It sits at a distance of a few tens of millions of light-years, close enough that individual member galaxies can be resolved in detail, and far enough that the cluster acts as a single dynamical actor in the regional flow. In the velocity field drawn from many distance measurements, the vectors in our quadrant of the sky tilt gently toward Virgo. The tilt is not steep. It is a soft gradient superposed on the broader currents that guide the local group through the surrounding web. That gradient registers as a modest but measurable component of the group's peculiar velocity and as a similar tendency among nearby groups to drift in the same general direction. The cluster's luminous heart is complex. Giant ellipticals dominate the central regions among them, Messier 87 with its enormous halo and its prominent jet and other massive spheroids that carry bright envelopes of old stars. Threads of hot, thin plasma fill the spaces between galaxies and glow in X-rays, signaling a gravitational well deep enough to hold gas at tens of millions of degrees Celsius. The luminous mass that shines in stars and gas is only a tracer. Most of the binding weight is dark. When that total is estimated by the motions of member galaxies by the temperature and distribution of the hot gas, and by the weak gravitational lensing that slightly distorts background galaxies, the sum reaches many hundreds of trillions of times the mass of the Sun. That weight is enough to bend regional streamlines, but not enough to dominate them alone out to the full distance of the local group. The effect is therefore gentle, an added inward component aimed toward Virgo that contributes to but does not define the overall drift. The signature of Virgo's pull appears with clarity in the pattern called Virgo-centric infall. Galaxies somewhat closer to the cluster than average show a tendency to move toward it faster than the pure background expansion would allow, while those somewhat beyond show a reduced recession in its direction because their peculiar velocity points back toward the cluster. Plot recession speed against distance along radial lines that pass near the cluster, and the curve deviates from the straight relation set by uniform expansion. Inside a certain radius from Virgo, the relation can even become triple-valued. A given recession speed corresponds to 3 distances, 1 for a foreground object, falling in 1 for a background object also falling in, and 1 for an object at a turning point near the so-called zero-velocity surface, where expansion is exactly balanced by the cluster's gravity. This pattern, long predicted by simple spherical models and refined by modern reconstructions, is seen in multiple independent distance indicators and provides a kinematic fingerprint of the cluster's influence. Measuring this pattern requires many well-calibrated distances across the sky sectors that pass through and around Virgo. Spiral galaxies supply one important rung through the correlation between their rotation speed and their luminosity. Elliptical galaxies add another through relationships among their size, surface brightness, and internal velocity dispersion. In nearby large galaxies, the graininess of unresolved star fields fluctuates in a way that can be translated into distance, when the population of stars is known, providing another rung that is especially effective in the smooth bulges of early-type systems. Where suitable evolved stars can be resolved, The abrupt brightening at the tip of the red giant branch furnishes a geometric tie. Each method brings scatter, but together they draw a coherent picture of the flow. Radio observations of neutral hydrogen cut through dust and crowding to recover spirals within the rich fields that lead toward Virgo, while infrared imaging maps the stellar content where the optical view is partially veiled. The resulting data reduce selection biases and bridge gaps on the sky, so that the flow lines can be traced cleanly into and out of the cluster's domain. The Virgo cluster is not a single relaxed sphere. It is a growing assembly with subclusters and infalling groups extended along the filaments that feed it. One subunit lags the main core and carries its own set of giant ellipticals. Other clumps approach along preferred directions. The hot gas shows irregularities and shocks that mark recent mergers. These internal complexities blur the idealized pattern of infall close to the center, but at larger radii the net effect on surrounding galaxies is simpler and more nearly radial toward the cluster as a whole. The local group lies well outside the region where Virgo's gravity cancels the background expansion. In this outer regime, the peculiar velocity caused by Virgo is a fractional addition to the group's overall drift, a component that points toward the cluster and that is shared by many neighbours within a similar solid angle on the sky. Quantifying gentle uses words here other than numbers, but in practice it means that when the local group's peculiar velocity is decomposed into pieces aligned with regional mass concentrations, the portion that aims toward Virgo is significant yet far from the total. Reconstructions that smooth the velocity field on scales of many tens of millions of light-years consistently show a broad convergent trend extending across our neighbourhood that cannot be explained by Virgo alone. At the same time, they agree that removing Virgo's contribution reduces the inward tilt along our line of sight by a noticeable amount. This middle ground, in which the cluster matters but does not dominate matches, the intuition one gains by simply inspecting the sky. Virgo is the nearest rich cluster, but it is not the only weight within the relevant hemisphere, and the flow lines that reach us are already shaped by structures both nearer and farther. The location of the zero-velocity surface around Virgo provides an additional ruler. Outside that surface, the smooth expansion wins, and galaxies drift outward on average, even while their peculiar components may lean inward. Inside it, gravity has overcome the background stretch and bound the material to the cluster. Distance surveys place this dividing shell well inside the range to the local group. That placement is a practical check on the gentle character of Virgo's pull here. The local group participates in Virgo-centric infall only in the weak outer sense, not as a bound satellite or as an object within the turnaround radius. As a result, the component of our peculiar velocity associated with Virgo is steady and cumulative rather than precipitous. The cluster's influence is anisotropic because it sits within a web. Streamlines that approach from directions aligned with feeding filaments can be stronger, and those that skirt large voids can curve more as they pass. The sky footprint of the Virgo-centric effect therefore depends on where one looks. In some longitudes, the inward tilt is clear, in others it is muted by competing gradients from nearby groups, or from walls that run nearly perpendicular to the line of sight. This directional dependence is not noise. It is the imprint of the surrounding structure modulating a central weight. When these angular variations are folded into the three-dimensional reconstruction, the resulting vector toward Virgo persists as a coherent contribution, while the smaller scale twists cancel in averages over large volumes. The language of attraction again invites restraint. It is easy to speak of the cluster pulling, but the field does not end at the cluster's edge, and the path of any given galaxy is shaped by the superposition of many sources of gravity. Virgo's role close to us is to add a local tilt that many nearby systems share. That tilt helps align the peculiar velocities within our neighbourhood and contributes to the sense of a common downstream direction. It does not by itself determine the overall course of the streamlines that stretch across hundreds of millions of light-years. In flow maps drawn in the rest frame of the microwave background and smoothed on scales, where linear approximations hold the cluster's signature as a localized inward fan centered on its coordinates fading gradually with distance, and stitched into larger bends imposed by more extended structures. As observations accumulate, the picture of Virgo's interior grows richer, yet the regional role remains steady. Deeper X-ray images reveal cavities and ripples in the hot gas carved by rising bubbles from the central galaxies. Radio maps show relic arcs and halos left by old shocks. Optical surveys extend the luminosity function down to faint dwarfs and map tidal features that trace recent accretion. All of these details inform the mass model near the centre. They refine the tie between observed light and total weight. But when the velocities are smoothed to the scales appropriate for large-scale motion, the precise internal state of the core matters little for the outer field. What counts for our purpose is the integrated mass and its position, both of which are established with enough fidelity to assign Virgo a clear moderate share of the local group's drift. This gentle share has practical consequences. When analysts remove modelled contributions from known nearby mass concentrations to study more distant influences, Virgo is among the first to be subtracted. Doing so sharpens the residual field and helps isolate slower gradients that stretch across larger domains. The success of this subtraction is judged by whether the remaining flow becomes smoother and more coherent on the sky, and by whether nearby groups show reduced scatter in their peculiar velocities after the correction. By these tests, Virgo's component is real and useful to account for, but its removal does not erase the downstream alignment seen over wide regions, confirming that other structures continue the work of shaping the flow beyond the cluster's reach. Set within the chosen outer to inner path, this is the scale to finish, before stepping inward again. The local group translates through the web with a vector that tilts toward Virgo among other directions. The cluster's mass adds a measurable inward component for many neighbours in this part of the sky. Its internal substructure complicates the very core, but leaves the outer signature of infall intact. Its zero-velocity surface sits well short of the local group, placing us in the weak regime where expansion dominates and attraction nudges rather than captures. With this gentle pull described and its limits marked, the map can move one notch deeper into the surrounding landscape, keeping the frame fixed, and the logic the same as the regional contributions are weighed in turn along the route that the streamlines trace. Between the nearby cluster landscape and the deeper convergences, the velocity field meets a broad foreground of weight that runs across our sky in linked arcs. This region is known by the names of its principal knots, Hydra and Centaurus, yet its dynamical role is not confined to any single knot. It is a wall of matter, a set of entwined filaments and cluster nodes, whose combined gravity bends trajectories over a wide solid angle. As the local group translates through space with its modest, peculiar velocity, the vectors around us show a gentle but organised swerve toward this foreground. The pattern emerges most clearly when many distances are gathered, and the flow is smoothed over scales of many tens of millions of light years. In that view, the foreground appears not as isolated cities of galaxies, but as a continuous continental shelf of mass that extends laterally, touches other shelves along saddles, and hosts multiple anchors where halos concentrate into clusters. The Centaurus sector presents one of those anchors. In the interior of this sector, giant elliptical galaxies sit within a hot atmosphere of thin plasma that glows in X-rays. The temperature and spread of that gas speak to a deep gravitational well whose binding weight is mostly dark matter. Galaxy orbits inside the well scatter in many directions under that deep pull. The luminous content is bright and crowded, yet it remains a tracer of a greater mass that neither shines nor absorbs light, and that defines the potential in which everything moves. The Hydra sector offset on the sky, but linked by the same wall, provides another anchor. Its galaxies move within a similarly deep envelope, and its hot gas registers comparable depths. Between and around these knots a dense weave of groups, filaments and sheets runs for great distances. The flow lines that cross this weave curve smoothly with no sharp deflections, because the gravitational landscape here is not a point-like attractor, but a stretched plateau with hills. A wall alters motion through accumulation. Every filament adds a slender thread of gravity. Every cluster adds a lump. The whole ensemble sums to a gradient whose range is large. The local group lies far enough away that none of the internal details of these nodes controls our path. What matters is the integrated field that their superposed weights create. In velocity reconstructions that respect the linear regime on large scales, the foreground appears as a long ridge with flow lines on its near side arcing gently toward it, running along its crest for a while in projection, and then continuing past it toward deeper interior regions of the same flow domain. This behavior matches the logic of motion on the cosmic web. Matter tends to move out of voids and onto walls. Along the walls, it tends to slide toward nodes. Beyond any one node, the motion persists under the guidance of still larger structures. The Hydra Centaurus foreground sits at the stage where wall and node conspire to reorient paths without ending them. The sky around this shelf is instructive because it juxtaposes high and low density regions. In the hemisphere where the local group's arrow points the wall, fills a sizable arc, and beyond it the eye meets further concentrations deeper in the same general direction. On the opposite side of the sky, broad underdense volumes open, and the peculiar velocities there display outward tilts that feed material back toward surrounding sheets. The contrast enhances coherence. Where a void releases matter, the neighbouring wall gathers it, and the presence of multiple cluster knots along that wall aligns surrounding vectors over a wide angular span. The result is a smooth field in which many independent galaxies share similar components of drift toward the same swath of longitudes, even though their individual environments vary. Observationally, the foreground demands a multi-wavelength approach. Starlight maps rich carpets of galaxies in optical imaging, but crowding and dust near the plane of the Milky Way can dim or hide systems that lie behind. Radio observations of neutral hydrogen pickup spirals, whose starlight is extinguished but whose gas still emits the characteristic line that radios through dust. Infrared surveys recover the stellar mass of galaxies with reduced sensitivity to obscuration anchoring distances in sectors where optical work alone leaves gaps. X-ray maps delineate the deep wells that mark mature clusters and active substructures, showing where gravity has heated gas to tens of millions of degrees Celsius. Weak gravitational lensing, though challenging in the nearby universe, adds a check on the total mass by tracking the tiny shears imprinted on background galaxy shapes, independent of how much light the foreground galaxies emit. When these windows are combined, the wall resolves into a connected landscape rather than a patchwork. In velocity reconstructions, the parts of the wall that lie behind the plane become tied in by these non-optical traces, so that the flow does not break artificially where the sky is hard to see. The Hydra Centaurus foreground is not static. Subclusters fall in along filaments, groups merge, shocks ripple through the hot gas, and the luminous galaxies themselves show traces of recent interactions in the form of shell streams and disturbed morphologies. These local details are the visible signs of ongoing growth, yet they do not disrupt the large-scale roll. Smooth to the scales appropriate for bulk motion, the wall maintains its identity as a broad gradient. Its internal inhomogeneities average out, and what remains is the weight distribution that steers paths across volumes far larger than any single cluster. In this sense, the foreground's effect on the peculiar velocity field is steady and cumulative. It adds a shared component to many neighbouring systems, including ours, without capturing them. A helpful mental picture comes from the idea of flow along a watershed. At high resolution, a raindrop may split around a small stone swirl in a tiny eddy, or pause in a shallow depression. At lower resolution, water on the same hillside still follows the general slope toward the valley. In the cosmic case, there is no medium and no friction, and the scales are much larger, but the framing survives. The wall provides a slope. Galaxies move under gravity's guidance along that slope, and their small-scale deviations wash out when many are averaged together to read the contour of the field. In maps drawn from thousands of distance measurements, the contour carries galaxies past Virgo's vicinity, and onto the broad Hydra Centaurus shelf before they angle further inward along the same basin's descent. The foreground also marks a place where neighbouring basins press against each other. The line that separates one basin of attraction from another rarely lies along an obvious luminous feature. It snakes through three-dimensional space where the velocity vectors flip from pointing one way to pointing another. Because the Hydra Centaurus wall is extended and strong, it influences the position of those separate traces, nudging the boundary surface between domains, without itself acting as the final destination. In practice, this means that galaxies near the far side of the wall may already belong dynamically to a neighbouring basin, even if their positions on the sky still place them among the same luminous filaments. This property emphasizes again that the dynamical map is made from directions and magnitudes of motion, not from where light looks thickest. Quantitatively, analysts fold the foreground into decomposition schemes that apportion the local group's peculiar velocity into components associated with nearby structures. A portion aligns with Virgo as already described. A larger portion aligns with the Hydra Centaurus shelf. That allocation depends on the smoothing scale and on how the mass field is parameterized, but across methods the result is consistent. This wall contributes a substantial share of the mid-scale guidance. Remove an estimate of its effect from the velocity field, and the residual arrows in this sector of the sky relax towards straighter lines aimed past the shelf, revealing the influence of more distant concentrations beyond. Leave it in, and the curvature emphasizes the wall's presence as an intermediate stage. Because distances remain the limiting factor in flow maps, the most effective catalogues for this region combine multiple indicators that perform well at the relevant ranges. Spiral galaxies with well-measured rotation speeds and line widths provide one rung. Early-type galaxies with tight structural correlations provide another. Surface brightness. Fluctuation distances add precision for smooth bulges. And where feasible, the tip of the red giant branch gives a geometric fix in the nearer parts of the wall and its outskirts. Grouping galaxies that share a common halo reduces the risk that internal motions masquerade as bulk drift. Volume-limited subsamples tame selection effects. Cross-checks against redshift surveys ensure that the density field inferred from motion is consistent with independent maps of how galaxies cluster. When all of these elements are assembled, the Hydra Centaurus foreground becomes one of the clearest mid-scale features in the nearby flow. The space around the wall shows how voids collaborate with walls to shape motion. On one side lie underdense volumes in which galaxies display outward peculiar components that feed into surrounding structures. On the other side, the density climbs toward additional filaments and nodes. The wall thus mediates between emptiness and crowding collecting matter from the low side and guiding it along ribs toward its richer knots. The local group does not sit on the wall, but faces it across a span in which the velocity vectors tilt that way. This perspective accounts for the shared directions seen among multiple nearby groups, and for the way streamlines drawn in the smoothed field tend to approach the sector, follow its grain in projection, and continue toward the interior of the same flow domain. Set within the discipline of moving from outer to inner scales, the Hydra Centaurus foreground is the next region after the local and cluster scales already established. It is more extended than Virgo, more complicated in detail, and more important for setting the mid-scale curvature of paths across our sky. Yet it remains a foreground. It does not define the final destination of the flow within this basin, only the current stage that reorients the drift and adds weight to the side of the sky toward which many vectors already point. By keeping attention on the field rather than on any single beacon, the description remains tied to the mechanics of motion. Arrows align because gravity is uneven, walls gather because voids return matter, and clusters mark the deepest hollows atop an already high plane. Within this view, the local group's path passes by the wall's influence, absorbs part of its guidance, and carries that guidance further inward along the same descent that the basin prescribes, ready for the next step that remains strictly within the same flow domain and the same frame. Across the plane of the Milky Way, where dust thickens and dense star fields crowd together, the background universe slips from easy view. Astronomers call this belt the zone of avoidance, because optical surveys once stepped around it, leaving a wedge of sky in which catalogues thinned and structures seemed to end abruptly at the glare of our own galaxy. The flow does not stop there. Streamlines pass through the plane, and any convergence that lies behind it continues to shape motions on our side. In this obscured sector sits a dense node of galaxies and hot gas that becomes visible only when methods change. It is the Norma cluster, a major mass concentration embedded in the same foreground wall already traced, and it occupies a central place in the mid-scale convergence that observers historically labelled the Great Attractor. The term is a shorthand. It suggests a single compact source, but the field here is not point-like. It is a region where several overlapping weights combine to bend paths with Norma as one of the deepest wells within that region. The position of Norma falls very near the Milky Way's midplane where dust lanes twist and bright stars scatter light across detectors. In visible wavelengths, many background galaxies are dimmed or hidden entirely, and faint sources blend into the wings of bright stellar images. The solution is not to accept the gap, but to switch windows. Neutral hydrogen in spiral galaxies emits a characteristic radio line that slips through dust, so radio surveys sweep the obscured belt and recover recession speeds and rotation widths for systems whose starlight is veiled. Infrared imaging pierces much of the extinction and restores stellar light from smooth bulges, allowing structural distance methods to be applied where optical work falters. X-ray maps trace the thin hot plasma trapped in the cluster's deep gravitational well, revealing the extent and temperature of the atmosphere that binds the system together. Weak gravitational lensing, though, more difficult at low redshift and in crowded fields, adds a light-independent estimate of total mass by tracking tiny shears in the shapes of distant background galaxies. Together, these windows fill the zone of avoidance with detections and distances enough to anchor the flow across the plane and to recover the node that optical photographs once missed. Dynamically, Norma behaves as a massive growing cluster. Member galaxies move within a deep potential, dominated by dark matter, and their velocities scatter around a central value set by that depth. The hot gas that blankets the cluster glows at tens of millions of degrees Celsius, and its pressure structure shows edges and ripples that mark shocks from recent accretion. Some luminous galaxies carry shells, tidal tails, or disturbed disks that record encounters along infalling filaments. These details complicate the core, but they strengthen the inference that the node is active and fed by the same wall and ribs that guide the surrounding field. Smoothed to scales appropriate for bulk motion, the internal scatter disappears into an integrated pull that is felt well beyond the cluster's bright centre. The role of Norma clarifies the meaning of Great Attractor. Flow reconstructions that combine many distances with a physically constrained inversion do not converge on a single beacon. They show a region of convergence in which several lumps of mass aligned along the Hydra Centaurus shelf, and its continuations work together to reorient the flow. In this picture, the arrows in the surrounding sectors tilt toward Norma and then arc beyond it, continuing toward deeper parts of the same basin, rather than terminating. The convergence is therefore regional and extended. Norma is a principal knot within it, not an isolated anchor that acts alone. This distinction is important because it preserves the outer to inner logic. The wall bends trajectories. The node sharpens the bend. The path carries on under the guidance of still larger scale structure that lies farther along the same general direction. Distances behind the plane demand special care. Standard candles that rely on blue light suffer heavy extinction, and structural methods that use smooth bulges require precise calibration of reddening across fields packed with foreground stars. Spiral galaxies become especially valuable because their rotation speeds measured in the radio tie to their intrinsic luminosities in a way that sidesteps much of the dust problem. The correlation is not perfect, but across large samples its scatter can be averaged down. For early type galaxies, relations among size surface brightness an internal velocity dispersion supply, distances that are less sensitive to extinction when observed in the near-infrared. Where suitable evolved stars are resolved, the sharp onset of helium burning at the tip of the red giant branch provides a geometric rung. Each indicator carries its own sources of uncertainty. The strength comes from overlap. In the sectors just above and below the plane where extinction falls, methods cross and 0 points can be checked against one another and then carried through the obscured belt. Selection effects are strong in the zone of avoidance and require explicit treatment. Obscuration favours detection of the brightest background galaxies and can bias average distances low if left uncorrected, creating a spurious sense of infall toward the observer. Analysts respond with volume-limited subsamples where the catalogues are dense enough, with modelling of the luminosity function in obscured fields, and with careful grouping so that galaxies sharing a common halo are represented by a single bulk motion, rather than by many internal orbits. Radio surveys that find neutral hydrogen preferentially select gas-rich spirals and undercount quenched systems common in cluster cores. Infrared imaging restores much of the stellar light, but crowded fields near the plane demand rigorous subtraction of foreground stars and diffuse emission. X-ray maps trace the hot atmosphere, but can miss cooler groups approaching along filaments. Weak lensing offers a total mass check yet suffers dilution, where bright stars reduce the usable background. None of these limitations invalidates the picture. They define the corrections and cross-checks that make the reconstruction robust, because the plane reduces the density of direct measurement simulations assume a greater role than usual in testing the field. Numerical models that evolve dark matter under gravity in an expanding background can be constrained to match the observed density outside the plane. Evolved forward, these constrained simulations predict a continuation of walls and nodes across the obscured sector and a convergence near Norma's location. Mock catalogues drawn from the simulations replicate the sky coverage, the distance indicator scatters, and the zone of avoidance mask. Running the same reconstruction methods on the mocks, and recovering the input field within uncertainties strengthens confidence that the real map is not an artifact of the gap. Where the mocks stumble, analysts flag similar regimes in the data and temper the conclusions. The result is a field that changes little when method samples or smoothing scales vary within reasonable bounds. That stability is a practical test for any purported convergence. The basin boundary near Norma adds another layer of insight. The dividing surface between neighbouring flow domains snakes through three-dimensional space where vectors flip direction. A map drawn purely from light would misplace that surface behind the plane because luminosity is incomplete. The velocity field cares only about motion, and therefore holds the boundary steady even where light fails. In practice, the reconstructed separatrix in this sector lies near the crest of the same wall that hosts Norma, with streamlines on our side arcing toward the node and then continuing inward through the basin that also contains the local group. Streamlines just beyond bend the other way and feed the neighbouring domain. The boundary is not marked by a single luminous feature. It is defined by the orientation of many small arrows, and in this obscured region those arrows remain readable because the methods that recover distances and velocities do not rely on blue starlight alone. For the local group, the practical outcome is a peculiar velocity shaped by several contributions that add coherently. A nearby component aims toward the Virgo cluster. A larger mid-scale component aligns with the Hydra Centaurus shelf. A reinforcing, more localized inward fan points toward Norma behind the plane. Removing an estimate of Norma's share from a reconstruction slightly relaxes the curvature of arrows in that sector, but does not straighten them fully because the wall remains, and because more distant weight continues to bend the field. Leaving it in strengthens the turn toward the plane, without changing the downstream fact that streamlines keep going. Either way, the reading is the same. Norma is not the terminus. It is a deepening of the slope along which the flow already runs. Norma's internal portrait supplies context without altering the outer narrative. Subclusters approach along preferred directions that follow the grain of the wall. Shock fronts in the hot gas mark places where an infalling group has passed or stalled. Extended faint features around galaxies point to tides that stretch them along the same directions that feed the node. These fingerprints explain why different windows sometimes disagree in detail. An X-ray map may show asymmetries where the gas is stirred. A radio map may see more systems along a filament rich in spirals, and an infrared map may emphasize the massive gas pore core. Smoothed to the scales relevant for bulk motion, these differences average away, and the underlying weight field persists. Placed within the present outer to inner path norma is the next necessary step after the wall. It is the obscured crossing, where the mid-scale structure tightens into a cluster knot, and it introduces the practical challenge of reading a flow through a veil. The challenge does not alter the rules. The frame remains the rest frame of the ancient microwave glow. The map remains a smoothed field of peculiar velocities tied to distances built on overlapping rungs. The aim remains to isolate what belongs to the basin from what belongs to the observer and to local internal orbits. With the hidden node weighed and its limits marked, the route can continue inward along the same descent toward the broader convergence that lies still farther along the path and that adds its own long-range guidance to the quiet drift of our galaxy and its neighbours. The phrase Great Attractor enters the literature as a practical label for a place on the sky where many independent velocity measurements point inward, yet the dynamics behind that label differ from the picture of a single, massive object that drags galaxies toward it. In the language of the flow, an attractor is a region of convergence in which streamlines of peculiar velocity sink toward lower gravitational potential when smoothed on large scales. The convergence occupies an extended volume. Within it, several clusters, walls, and filaments overlap in projection and in three-dimensional space. The weight that guides motion is dominated by dark matter with luminous matter as a tracer. The local group approaches this region along a gentle gradient that begins far outside, bends across the foreground shelf of Hydra, and Centaurus tightens near the obscured node around the Norma cluster, and continues inward beyond. The continuity of that path is the essential property. The flow does not terminate at any one bright knot. It threads through them because each knot sits within a larger descent. In a reconstruction that respects the scales where linear theory holds and where random local orbits are averaged away, the convergence appears as a broad bowl whose rim is set by saddles connecting neighbouring basins. Streamlines approach from many directions, slow, slightly near dense knots, where the field steepens and then resume along the combined gradient. The presence of a bowl rather than a spike follows directly from how mass is arranged in the nearby universe. Dark matter halos merge hierarchically and are embedded in filaments that feed them. Clusters grow where several ribs meet, but the ribs and the surrounding wall carry a substantial portion of the mass. Gravity responds to the total. The shape of the peculiar velocity field therefore reflects the extended structure more than any one core. This property explains why early searches for a single extraordinary cluster that could account for all of the observed drift did not succeed. The field required by the data does not belong to a solitary beacon. It belongs to a connected landscape. The way convergence is measured underscores this point. Distances are used to subtract the smooth expansion from recession speeds. The residual supply radial components of peculiar velocity. Those components are then integrated into a three-dimensional field under the assumption valid on large scales that the flow is nearly curl-free, because gravity has had time to erase vorticity generated by small-scale interactions. The recovered field is smoothed over many tens of millions of light-years to remain within that regime. When this process is applied to catalogues that bridge the zone of avoidance with radio-infrared and X-ray selections, the vector field on our side of the plane angles toward a swath centered near the constellations that mark the Hydra-Centaurus wall and the Norma node, and on the far side it continues showing that the deepest descent lies beyond any one visible system. The fact that the direction persists when independent methods and independent distance indicators are used is a practical test. A real convergence retains its identity when inputs change within reasonable bounds. The meaning of pull in this context is mechanical rather than metaphorical. A peculiar velocity is the integral of small accelerations over long times. Those accelerations are set by gradients in the gravitational potential, which in turn is set by the distribution of mass. Most of the mass is dark. The luminous map is therefore an incomplete guide, especially behind the plane where starlight is dimmed. The velocity field does not care about light, it cares about weight. When many residual vectors aim the same way across a wide volume, they reveal the presence of an extended gradient. When they curve gently across a region and then keep going, they reveal that the region is part of a larger descent. In this reading, the Great Attractor is the name given to a mid-scale convergence embedded within the larger basin called Laniakea. It is not a sink that swallows motion, it is a saddle-backed hollow within a broader valley. The concept of a zero-velocity surface helps organize the geometry. Around a sufficiently massive cluster, there exists a bounded region, inside which the background expansion no longer wins, and matter turns around to fall inward. Around Virgo, that surface lies at a modest radius compared with the distance to the local group. Around the Great Attractor region, there is no single spherical turnaround tied to a single core, because the mass is spread along walls and nodes. Instead, there are local turnarounds around individual clusters and groups nested within a larger volume, in which the expansion still dominates on average, while the peculiar component aims inward. The local group dwells in that larger volume. It is not bound to the mid-scale structures. It responds to them with a steady drift superposed on the universal stretch. Uncertainties in distance propagate into the reconstructed field, and the zone of avoidance imposes a geometrical mask. These complications are addressed in two complementary ways. First, overlapping distance indicators with different systematics are combined, and galaxies likely to share a common halo are grouped so that internal velocity dispersions do not masquerade as bulk motion. Second, prior knowledge about the smoothness of the large-scale flow is encoded in the inference so that poorly constrained regions do not sprout artificial structure. The outcome is not a sharp map with edges and corners. It is a conservative portrait that emphasizes coherent features. In that portrait, the Great Attractor region holds its place. Its center shifts by a few millions of light years depending on the data set and the smoothing length. Its angular extent broadens or narrows with the catalogue, and its interior shows different emphases depending on which wavelength highlights, which traces, yet the broader convergence remains. Independent data offer checks. Redshift surveys outline the three-dimensional distribution of bright galaxies and reveal the walls and clusters that likely host much of the mass. X-ray observations mark the deepest wells where hot atmospheres sit. Weak lensing where feasible supplies a light-independent measure of total matter. Constrained simulations tuned to match the observed density field outside the zone of avoidance predict that a continuation of the Hydra Centaurus shelf and its knots lies behind the plane, and that streamlines in the neighbourhood should arc toward a region near Norma before continuing. Mock catalogues derived from those simulations, when subjected to the same masks and the same reconstruction algorithms as the real data, recover a convergence similar in position and character to the one inferred from observations. These cross-checks do not replace data. They act as consistency tests that the reconstructed field is compatible with how gravity should shape motion in a universe with similar large-scale structure. A useful diagnostic of convergence is given by the velocity shear field, which measures how neighbouring vectors change in direction and magnitude. In regions dominated by divergence, vectors spread apart, and the field carries matter away. In regions dominated by convergence, vectors come together and the field guides matter inward. Around the Great Attractor, the shear pattern registers a broad inward tendency over a large volume rather than a sharp inward spike. This matches the extended character of the mass distribution and contrasts with the more compact shear found near the cores of individual rich clusters. The pattern also shows that the convergence is anisotropic, stronger along certain longitudes that follow the grain of the wall and the ribs that feed it, and weaker across directions that face large voids. The anisotropy explains the sky maps in which some sectors exhibit pronounced inward tilts, while others show milder bends. The role of still more distant weight enters at this stage. Farther along the same general direction as the Great Attractor lies a much larger concentration of clusters and superclusters, commonly called the Shapley concentration. Its integrated mass is sufficient to add a long-range component to the flow that passes through the Great Attractor region. In reconstructions that include wide areas and that decompose the local group's peculiar velocity into contributions from shells of increasing radius, a non-trivial share appears to arise from distances well beyond the mid-scale convergence. That share does not negate the Great Attractor's influence, it complements it. The mid-scale region orients and focuses the streamlines, while the far field adds a slow, persistent acceleration that continues beyond. This layered guidance is expected in a basin whose descent extends from the outer periphery to deep interior structures. For the local group, the practical implication is steady. Its peculiar velocity contains components that can be associated with Virgo, with the Hydra Centaurus shelf with the Norma node behind the plane, and with still farther concentrations. The sum points toward the Great Attractor region and beyond, and its magnitude fits within the pattern observed among many neighbouring groups that share similar directions. Subtracting modelled contributions from nearby structures reduces the curvature in their sectors, but does not erase the overall alignment across the sky, indicating that the remaining flow is guided by the more extended field. Leaving the nearby contributions in shows how the mid-scale convergence sharpens the turn and organises local vectors. Either approach reads the same underlying map, a basin with a broad interior toward which motions incline. The discipline of staying within the current region fixes the scope. The Great Attractor is the name used for a convergent zone inside Laniakea, where multiple weights combine to bend paths. It is not the centre of the basin, and not a single object. Its significance arises from the coherence of motion it imposes across a wide space, and from the way it sits at the crossroads of major filaments that thread the sky behind the Milky Way's plane. Its obscuration explains why early optical catalogues fell silent across longitudes where the field remains active. Its recovery in radio infrared and X-ray surveys and its persistence in velocity, reconstructions that average over method and mask anchor it as a dynamical feature rather than a photographic one. With this definition in place, the path inward can proceed without changing frames or methods. The microwave background still supplies the universal rest frame. The subtraction of the smooth expansion still isolates the peculiar field. Distance ladders still tie together many rungs so that individual scatter averages down to reveal coherent trends. The convergence just explored remains a regional feature embedded within the same basin, and it prepares the route for the next inward step where the influence of even more distant mass begins to make itself felt across the same streamlines that cross the Great Attractor's domain on their way toward deeper interior structures. Farther along the same general direction as the mid-scale convergence lies a deeper assembly whose reach is felt across a large fraction of the nearby universe. Astronomers call it the Shapley concentration, a crowded expanse of superclusters and rich clusters that knots the cosmic web into a high plateau of mass. In maps that colour only by starlight, it stands out as a thicket of bright systems spread over many tens of degrees of sky. In dynamical reconstructions that weight everything by gravity rather than by light, its influence appears as a broad, slow gradient that adds a persistent component to the peculiar velocity field. The local group and many of its neighbours translate through space with a modest drift that points toward the mid-scale convergence and continues onward. The Shapley concentration strengthens that onward pull. It does not overturn the nearer guidance from the Hydra Centaurus wall and the Norma node. It layers a long-range acceleration beneath them the way a distant slope continues even after a walker passes over small hills. The character of this distant weight follows from scale. A single rich cluster can trap its own galaxy's heat gas to tens of millions of degrees Celsius and bend light from background sources. A concentration of many such clusters strung along filaments and folded into walls acts differently at our distance. It does not capture, It steadies the direction of travel across a wide region by adding a large-scale potential gradient that varies only gently across the sky. In the reconstructed velocity field smoothed over very large volumes, streamlines that approach the Great Attractor region do not end there. They arc through and keep going along directions that align with the distant concentration. The curvature is weak because the distance is great, but the coherence across broad angles reveals that the contribution is real and cumulative. Several observational threads tie this picture together. All sky redshift surveys chart the three-dimensional distribution of luminous galaxies and mark a far hemisphere thick with clusters and superclusters in the sector associated with the concentration. X-ray catalogues reinforce the impression by flagging many hot atmospheres that signal deep gravitational wells. The space density of such wells in that direction exceeds the average seen over other longitudes at comparable depth, and the clustering of the richest system stands out. Weak lensing is difficult at these ranges for nearby observers, yet where measured it supports the presence of extended mass that does not depend on starlight. None of these maps alone yields motion. They supply context for the mass field. Motion enters when distances are used to subtract the smooth expansion and to isolate residuals that point toward gravity. When that kinematic information is added, the long-range alignment of peculiar velocities toward the sector deepens the case that the distant plateau contributes a non-trivial share of the flow. A practical way to quantify this share is to decompose the measured peculiar velocity into concentric shells. One starts with contributions from the nearer structures, then adds shells that extend to progressively larger radii, and one asks how much of the local group's vector is explained at each step. The first shell collects nearby groups and the virgocentric component. The next shells gather the wall and the obscured node. Subsequent shells widened to accommodate the sparser sampling at greater distances add the far concentration. In analyses that enforce smoothness at each scale, and that guard against biases in distance selection, a significant residual remains after the mid-scale contributions are removed. That residual aims along the same longitudes as the Shapley sector, and declines only slowly as shells expand to include it. The interpretation is conservative. The method does not assign the entire residual to any single feature beyond the mid-scale convergence. It notes that the addition of the far concentration reduces the residual in a manner consistent with the combined mass visible in redshift and X-ray maps, and with the continued alignment of peculiar velocities in its general direction. The long reach of this sector appears also in the pattern of bulk flows measured for ensembles of galaxies or clusters within large volumes. A bulk flow is the average peculiar velocity of many objects within a region. When measured across volumes that span many tens to a few hundreds of millions of light-years, such averages reveal whether there is a preferred direction of motion beyond local noise. The presence of a distant concentration does not yield a sharp apex that dominates every neighbourhood, but it does bias these averages in its favour. Regions pointed toward the sector tend to show a small excess in that direction. Regions pointed away tend to show less. The differences are modest, yet they persist across independent catalogues and methods when care is taken with selection effects and with the grouping of galaxies to remove internal dispersions. Their persistence suggests that the far field is not a minor correction. It is one of the organising tendencies of motion on the larger scales accessible to the distance ladder. Uncertainties grow with range. Distance indicators lose precision at great depths because standard candles become faint, and structural correlations broaden, and because the sampling becomes sparse. The zone of avoidance also widens in comoving angle, with distance making the obscured wedge on the sky subtend a larger physical width. Analysts compensate with several strategies. They combine indicators with different sensitivities, so that systematic errors tend to cancel when averaged. They create mock catalogues from constrained simulations that reproduce the observed galaxy density outside the obscured wedge, and then evolve the field forward, checking whether the flow through the mid-scale convergence aligns with a distant plateau similar in position and richness to the Shapley sector, They downweight regions dominated by noise through filters that privilege coherent features supported by neighbouring measurements. They test whether the broad direction and amplitude of the inferred far component remain stable when individual rungs of the distance ladder are removed, or when the smoothing scale is varied within reasonable bounds. Stability under these changes is used as a practical criterion that the distance share is robust. The language of attraction again benefits from care. It is tempting to imagine the far concentration as a massive beacon that pulls in a simple radial way. At our location, the field it produces is closer to a background slope. The slope is not perfectly uniform because the concentration itself is structured with multiple knots and bridges, but the gradient it creates across our neighbourhood changes only slowly with position. The result is a near constant addend to the peculiar velocity vectors of many groups spread over a large angular sector. That addend does not erase the influence of nearer weights. It sets the stage upon which nearer weights draw their sharper bends. In that sense, the distant plateau organises motion by providing a common far horizon toward which the mid-scale streamlines already point. The role of voids surrounding the concentration helps explain the geometry. Immediately around dense clusters lie filaments that feed them. On larger scales, these filaments and walls border wide underdense volumes. Matter tends to flow out of those volumes and toward the surrounding structures. Seen from our vantage, some of the largest underdensities lie on sky sectors opposite the concentration. Their presence moderates any countervailing pull from that side, so the net long-range gradient tilts the field toward the richer hemisphere. This configuration echoes the mid-scale picture in which a wall mediates between emptiness and crowding. At great depth, the same theme repeats with larger cast. Broad voids loosen their hold walls and clusters collect, and the sum of many small accelerations points gently toward the side with more weight. Cross-checks that do not rely directly on the distance ladder can support the inference in ways that remain within the dynamical frame. The temperature and distribution of hot gas in the richest clusters in the sector indicate large masses when interpreted through hydrostatic equilibrium, anchoring the weight budget independently of starlight. The abundance of very luminous clusters in that direction, compared with other directions at similar depth, when calibrated against expectations from large simulations of structure formation, suggests that the sector lies on the tail of the mass distribution, and so is likely to exert a measurable pull. Measurements of small kinematic imprints on microwave backgrounds through scattering by moving clusters, while challenging, can in principle constrain the bulk motion of those clusters and offer a complementary route to long-range flow. Each of these threads carries its own assumptions and limitations, but together they converge on a consistent message that the distant plateau matters for the direction of motion on the larger scales. For the local group, the practical sum is a vector composed of layered contributions. The nearest shell adds a component toward Virgo. The mid-scale shells align with the Hydra Centaurus wall, and with the obscured node near Norma. Beyond them, the shells that include the Shapley concentration add a slow but persistent push in approximately the same general direction. The resulting arrow is not the property of any one named structure. It is the integral of many. When analysts remove modelled contributions from the near and mid scales, the residual retains a preferred orientation that points toward the far plateau. When they include the far plateau, the residual diminishes, and the overall field becomes more nearly isotropic on the largest accessible scales. This behaviour is what one expects if the distant concentration is the correct far field to include in a basin-wide descent. Adhering to the outer to inner path, this is the moment to mark the limits of the far share, and to return our attention to the domain within which the Milky Way resides. The Shapley concentration does not define the boundary of the basin. It sits within the same network that outlines Laniakea and its neighbours, and its long-range guidance adds to the coherence already impressed by nearer structures. Its relevance in this narrative is to show that the basin's descent extends across many hundreds of millions of light-years, and that the path traced by the local group is consistent with a superposition of gradients that change character with scale but align in direction. With the far slope acknowledged and its role distinguished from the mid-scale convergence, The next inward step can address how obscuration and survey windows shape our maps, and how the combination of methods stitches the sky into a continuous field without leaving holes where the galaxy's plane crosses our view. Surveys across the sky do not see the same universe. Each window favours some objects, misses others, and measures different properties with different kinds of uncertainty. Dust in the Milky Way absorbs and scatters blue light and dense star fields near the galactic plane crowd detectors with foreground sources that hide faint background galaxies. Emission and absorption from gas in our galaxy complicate spectra. These effects peak along the equator of the Milky Way and toward the bulge, producing a zone of avoidance where early optical maps left a wide gap. The velocity field does not respect that gap. Streamlines cross the plane, and any convergence that lies behind it continues to shape motions on our side. The task is to change windows, stitch catalogues, and calibrate distances so that the map remains continuous where the photographs once went quiet. Infrared imaging addresses extinction at the source. Longer wavelengths traverse dust with smaller losses, so near-infrared surveys recover the smooth light from old stars in galaxy bulges and disks behind the plane. Structural distance methods that depend on the texture of unresolved stars work well in this regime. The fluctuation of surface brightness from one resolution element to the next decreases with distance in a predictable way, and when the stellar population is characterized, the fluctuation amplitude becomes a standardizable ruler. In large early-type galaxies, the sharp onset of helium burning at the tip of the red giant branch offers another rung. Its apparent brightness gives a geometric distance once foreground reddening is modelled. These tools allow distances to be measured across sectors where optical work alone would falter, and they carry the ladder's 0 point through obscured longitudes by direct overlap with clearer lines of sight. Radio observations add a complementary view by targeting neutral hydrogen in spiral galaxies. The characteristic spectral line from this gas passes through dust with little attenuation, so galaxies hidden in optical photographs reappear in radio maps. The frequency shift of the line yields a recession speed even where starlight is veiled. The width of the line traces rotation speed, and when combined with a measure of total brightness, the empirical relation between rotation and luminosity yields a distance. For any single system, the scatter is significant, but across large, well-selected samples, the mean relation tightens and becomes a reliable rung. Because radio selection favours gas-rich spirals, it fills a different portion of the galaxy population than infrared selection, and the two together reduce the chance that a single bias steers the map. X-ray observations mark the deepest gravitational wells by revealing thin hot plasma bound in cluster potentials. Gas at tens of millions of degrees Celsius emits strongly at high energies, and its pressure structure outlines shocks, subclusters, and recent mergers. Although these data do not by themselves give distances to individual galaxies, they anchor the mass model for clusters that bend the surrounding flow. A sector of sky with an excess of bright hot clusters is a sector with above-average weight. When such sectors align with inward tilts in the reconstructed velocity field, the consistency strengthens the interpretation that gravity from extended structure guides the motion. Visible light remains essential where extinction is low. It supplies sharp images and spectra for calibrating the basic rungs of the distance ladder. Parallax within the Milky Way sets an absolute scale for nearby stars. Certain periodic variables whose pulsation period tracks intrinsic brightness extend the ladder to nearby galaxies. Explosive transients whose peak brightness can be standardized by the shape of their light curves push the ladder farther in select directions. Structural correlations among size surface brightness and internal velocity dispersion in smooth early-type galaxies furnish distances at ranges that bridge to clusters. Each rung carries its own sources of error, yet the strength of the ladder lies in overlap. Where two methods share the same targets, 0 points are checked. Population effects are constrained, and systematic shifts are exposed. Selection effects pervade all windows and must be modelled. Flux-limited samples favour brighter objects at larger distances, which can bias mean distance is low and manufacture an artificial sense of infall toward the observer. Correcting this bias requires estimates of the luminosity function for each tracer population and an explicit account of how survey limits translate into volume coverage. Volume-limited subsamples help when catalogues are dense enough. Grouping galaxies that share a common dark matter halo prevents internal orbital speeds from masquerading as bulk drift. Masks near the plane must be carried through every stage of the analysis, so that missing sectors do not produce false asymmetries in the inferred field. The zone of avoidance is treated as a mask, but it is not a void. Radio and infrared surveys populate the masked longitudes with galaxies and clusters whose positions and recession speeds are measurable. Distance indicators that perform well in the near-infrared can be applied on both sides of the plane and across windows, where foreground effects are modest, creating bridges that carry the scale through the obscured belt. Foreground stars are modelled and subtracted to reduce confusion. Extinction maps derived from dust emission and star colours give spatially varying corrections, so that the same intrinsic object is not assigned different distances, solely because it lies behind a thicker lane. Where the foreground remains intractable, the map accepts reduced weight rather than inventing structure. All sky redshift maps provide an independent backbone for the mass distribution. They record where galaxies reside in 3 dimensions, under the assumption that redshift mostly tracks distance through expansion, with caution where peculiar velocities are large. These maps reveal walls, filaments, and clusters on both sides of the plane and flag likely continuations across the obscured wedge. The velocity field derived from distances is then compared with the density field derived from redshifts under a simple large-scale relation between how fast matter converges and how much the local density exceeds the average. Agreement in phase and amplitude within quoted uncertainties is a practical test that the reconstruction has captured the main features without overfitting noise. Weak gravitational lensing adds a light-independent measurement where feasible. The total mass along a line of sight slightly shears the shapes of background galaxies. Averaged over many sources, the shear pattern maps projected mass without regard to how much starlight the mass emits. Near the plane, bright stars and dust reduce the usable background and complicate measurements, but away from the most crowded fields, lensing can check whether features in the reconstructed density field are plausibly heavy. Where lensing detects a ridge that also bends, streamlines the case for a true gravitational slope strengthens. Simulations enter to test methods and stability. Starting from initial conditions that match the statistical imprint of early density fluctuations, numerical models evolve dark matter under gravity in an expanding background, and where feasible include gas physics for the luminous component. From such models, one can generate mock skies that match the actual survey footprint's flux limits, distance indicator scatters, and the mask of the zone of avoidance. The same reconstruction algorithms used on the data are then run on the mocks. If the recovered flow and density fields match the known input within uncertainties, confidence rises that the methods are faithful. If the methods stumble in certain regimes, those regimes in the real data are flagged for caution or excluded from interpretation at small scales. This cycle keeps the final map conservative and emphasizes only coherent features that persist under changes in selection, smoothing and calibration. Reference frames are handled consistently across windows. All measurements are shifted into the rest frame in which the cosmic microwave background appears uniform, so that the observer's motion does not imprint a false dipole on the catalogues. Internal motions within bound systems are averaged out by replacing clusters or groups with single bulk values, so that the hot random orbits inside a cluster do not inflate the large-scale drift. 0 points are checked by comparing distances to the same galaxies derived through different indicators and through independent instruments. Temporal baselines are accounted for when combining surveys taken years apart, so that small calibration drifts do not propagate into coherent false flows. The resulting velocity field is intentionally cautious. It emphasizes coherence on scales where linear approximations hold, and where the link between the divergence of the peculiar velocity and the underlying density contrast remains valid. It avoids overinterpreting noisy sectors and carries explicit uncertainties that widen across the plane and at great depths. Within those limits, the field shows continuous streamlines that cross the galactic equator, a broad convergence in the mid-scale region historically labelled the Great Attractor, and a persistent long-range gradient that aligns with the far concentration of clusters farther along the same general direction. Features that fail to survive changes in method mask or smoothing length are treated as provisional and are not used to set the path. For the present narrative, the purpose of these windows is practical. They ensure that the path from outer to inner scales does not jump across blind sectors or rely on a single tracer. They keep the frame fixed as the description passes from the local group to the nearby cluster environment across the foreground wall, through the obscured node and onward toward the deeper interior of the same basin. The methods that bridge the zone of avoidance also stabilize the map in less obscured regions by averaging away small local irregularities that would otherwise distract from the large-scale flow. In that way, the same discipline that repairs the gap behind the plane also clarifies the field where the sky is clear. With these observational foundations in place, the path can move inward while remaining within the same domain. The next scale is the modern delineation of the basin itself, in which flow lines define the outer boundary, ridge lines divide dynamical watersheds, and the domain that contains the Milky Way is mapped by motion rather than by light. That step keeps the same rules already in use. Stay within the current region, proceed from the outer layers to the inner layers, and let gravity, not a catalogue of bright objects, set the direction of travel. A basin of attraction is not drawn on a photograph. It is traced by motion. In practice, that tracing begins with a catalogue of distances and recession speeds spread across the sky and out to ranges where peculiar velocities remain measurable. The expansion is subtracted to leave residuals that point toward gravity. Those residuals are then integrated into a continuous three-dimensional velocity field after the data are smoothed on scales where random orbits cancel and where linear relations between flow and mass remain adequate. From that continuous field, streamlines are followed the way lines of current are followed in a steady river. Where many streamlines bend inward toward the same interior, a basin appears. Where neighbouring streamlines diverge and feed a different interior, a boundary is crossed. When this procedure is applied to the nearby universe with modern catalogues, the domain that contains the Milky Way takes a coherent shape. It occupies a broad volume stitched together from filaments, walls and clusters, and its streamlines drain toward a shared interior rather than toward many isolated points. The label given to this domain is Laniakea. The name is a convenient tag. The definition rests on dynamics. The delineation proceeds by identifying separatrices, the thin three-dimensional surfaces, where the direction of motion flips from one interior to another. A useful way to visualize those surfaces is to color the velocity field by the direction of its vectors after smoothing, and then to mark the loci where neighboring vectors sampled on a grid no longer point toward the same interior. In places where data are dense, the surfaces are traced directly by the measured flow. In places where data are sparse, the reconstruction enforces smoothness, consistent with gravity's action on large scales, so that unmeasured regions do not generate artificial knots or voids. The result is a dynamical watershed, a closed domain bounded by ridgelines in the velocity field. Inside that boundary, galaxies drifting under the present gravitational landscape follow paths that, when extended, converge toward the same region. Outside paths feed neighbouring domains. This watershed is not spherical. It winds around voids that release matter, climbs gently across shelves, where the net gradient points inward, and threads along filaments where the flow is strongest. Along its rim lie saddles, where the gradient is shallow, and the choice between downstreams is most delicate. The sensitivity of those saddles to details makes the boundary patchy, where the data thin yet the gross outline remains stable under changes in the smoothing scale, or in the set of distance indicators included. Stability under such changes is a practical criterion that the basin is real. If a domain vanishes when one rung of the distance ladder is removed, or when the grid is shifted slightly, the map is overfitting noise. If it persists, the map is reading a coherent feature of the large-scale flow. Within Laniakea, the reconstructed field shows streamlines that cross the local group's neighbourhood, tilt gently past the Virgo cluster, rather than stopping there, curve across the Hydra Centaurus shelf, tighten near the obscured node around Norma, and keep going toward a deeper interior. The pattern respects the earlier steps because it is derived from the same kinematic logic, now applied to the whole region at once. The basin's interior is not a point sink. It is an extended zone of convergence set by the superposed weight of many halos embedded in the cosmic web. The far field from the distant plateau of rich clusters strengthens the overall tilt but does not define the boundary. The boundary is local to the domain and is drawn by the orientation of motion there. Neighbouring domains on the far side of the watershed drain toward their own interiors that lie in different directions, and the separatrix snakes between them like the crest between two catchments on a mountain range. Because most mass is dark, the luminous map is an incomplete sketch of the basin. The velocity field is more faithful because it responds to total weight. In practice, the reconstruction uses galaxy distances for kinematics and galaxy redshift maps for context, with a simple large-scale relation between the divergence of the peculiar velocity and the contrast of matter density supplying the physical tie. The tie is applied after smoothing over scales where nonlinear small-scale motions are washed out. In dense clusters where random orbits dominate the field is not forced to resolve internal structure, those regions are treated as single actors with bulk velocities. This deliberate coarseness keeps the map in the regime where the link between flow and mass remains reliable, and where the concept of a watershed is meaningful. The clarifying power of the basin picture lies in the way it connects disparate features under a single rule. The local group is no longer an isolated arrow. It is a sample point on a streamline that shares its direction with many neighbours. The Virgo cluster is no longer a candidate for an ultimate destination. It is a mid-scale weight that adds an inward component within the same domain. The Hydra Centaurus shelf is no longer an unrelated wall. It is a sloping surface inside the basin that reorients paths without enclosing them. The obscured Norma node is no longer a missing piece behind the plane. It is a visible deepening of the same descent when read through radio infrared and X-ray windows. The distant plateau of clusters is no longer a remote curiosity. It is a far-field gradient that biases the downstream direction across the basin. The boundaries of Laniakea emerge not from drawing lines around luminous concentrations, but from marking where motion itself separates. Uncertainties are carried explicitly through this process. Distance errors propagate into peculiar velocity estimates. The zone of avoidance introduces anisotropic sampling. The reconstruction counters by grouping galaxies that share a halo so that internal dispersions do not inflate the large-scale field, by employing smoothing lengths tuned to suppress noise while preserving coherent features, and by comparing results across multiple independent distance indicators. Where the separatrix is poorly constrained, the map shows broader uncertainty bands rather than sharp surfaces. Where the data are strong, the boundary tightens. Consistency checks include verifying that the basin's interior does not shift dramatically when the catalogue is perturbed with quoted errors or when different regularization strengths are used. The persistence of the domain under these changes supports the inference that the Milky Way resides within a genuine dynamical catchment. The geometry of Laniakea includes voids that play an active role. Under dense regions are not passive gaps. They push by their absence. Matter flows out of them along the shortest path to surrounding walls and filaments. In the watershed view, these outward flows act like tributaries in reverse, feeding the basin's internal structures from below rather than from above. The pattern sharpens the boundary because vectors within a void point away from its centre toward different surrounding walls, and along the dividing ridgelines those vectors tilt toward different downstreams on either side. The result is an edge defined by the orientation of outward motion as much as by inward pull. The centre of the basin is a construct of the flow, not a single luminous core. It is the region where streamlines after smoothing show minimal divergence and maximal inward tendency over the largest accessible scales. In a static, isolated system, such a centre might coincide with a dominant cluster. In the real nearby universe, the centre is distributed because the mass that shapes it is distributed. The reconstructed map therefore labels an interior zone rather than a point. Practical uses of this zone include defining a rest frame for comparisons testing simulations against an observed dynamical domain and apportioning the local group's peculiar velocity among contributions that arise within and beyond the basin. When the field is expressed in the frame where the cosmic microwave background looks uniform, the basin center provides a second regional frame, aligned with the dynamics of our neighborhood. The value of naming the basin lies not in the label but in the discipline it imposes. With a watershed defined by motion, the narrative can proceed inwards step by step without jumping scales. It can ask at each radius from the local group which structures add coherent components to the downstream direction, and how those components combine under gravity to guide paths. It can treat obscured sectors with the same tools as clear ones, because the definition is kinematic rather than photographic. It can compare observations to numerical models that evolve matter and motion together, and that can be constrained to resemble the observed density field outside the masked regions. In those comparisons, mock skies that include a basin like Laniakea, and neighbours like its adjoining domains reproduce the broad features of the reconstructed field, when the same smoothing and the same masks are applied, strengthening confidence that the watershed is not an artifact of method. The basin picture also sets limits. It does not claim that every small object within the domain participates smoothly in the large-scale flow. Groups bound to massive clusters can have internal motions that deviate strongly from the coarse field near their centres. Tidal interactions between close pairs can sling galaxies onto paths that wobble with respect to the smooth direction. The map acknowledges these realities by staying at the scales where the relation between flow and mass is valid, and by averaging over local noise. In the averaged view, the local group's vector sits in a field that is continuous across the sky, crosses the galactic plane bends in predictable ways near known concentrations of mass, and remains aligned with a far horizon defined by an excess of weight. With Laniakea delineated as a dynamical watershed, the outer to inner path gains a firm container. The local group resides within it. The mid-scale convergence historically labelled the Great Attractor lies inside it. The foreground wall and the obscured node are interior features. The far plateau contributes a long-range gradient that continues across its breadth. The separate traces that bound neighbouring domains lie along ridges where the direction of motion flips. Within these bounds, the next inward step can focus on the invisible actor that sets most of the weight in the first place. Dark matter defines the backbone upon which luminous galaxies hang, and its distribution more than the starlight sculpts the gravitational potential that the velocity field reads. Turning to that invisible component keeps the frame and the discipline unchanged, while shifting the attention from traces to the mass that the traces reveal by their motion. The weight that shapes the basin is mostly invisible. Stars and gas mark only a small share of what gravity counts. The rest is dark matter, a component that does not shine and does not absorb light, yet outweighs ordinary matter by a wide margin. Its presence is inferred from motion, and from light deflected as it passes near mass. Spiral galaxies rotate too fast in their outer parts for the observed starlight alone to bind them. Clusters of galaxies hold hot gas at temperatures that require deeper wells than their stars can provide, and background galaxies appear slightly sheared around foreground structures in a way that traces total mass rather than just what glows. Each of these threads points to the same conclusion. The architecture of the cosmic web and the flow that moves along it are set chiefly by dark matter, with luminous matter riding as a tracer. In simulations that evolve matter forward from early, nearly uniform conditions, dark matter collapses first because it interacts primarily through gravity. It gathers into halos whose density peaks near their centers and fades gradually outward, and those halos link along filaments and sit at the nodes of walls. Gas falls into the same potential wells, cools where it can, and forms stars. The stars then light up the crests of the invisible scaffolding. Where the halos are deep clusters, grow and retain a hot, thin atmosphere at tens of millions of degrees Celsius. Where the halos are modest galaxies like the Milky Way form disks and bulges. The match between this simulated web and the observed clustering of galaxies is close when the relation between light and mass is allowed to vary from place to place. That variation matters in a dynamical map. It means there is no single conversion from starlight to weight. A region rich in faint galaxies can outweigh a region with fewer but brighter systems. The velocity field is immune to that confusion because it responds to all mass at once. On the scales where the basin is defined, the flow remains gently varying. In that regime, a simple tie links the divergence of the peculiar velocity to the contrast in mass density after smoothing over tens of millions of light years. Where matter is denser than average, streamlines tend to point inward. Where matter is underdense, they tend to point outward. Because dark matter dominates the density, it also dominates the gradients that direct motion. The luminous map becomes a guide only when corrected for how galaxies populate halos. Redshift surveys show where galaxies gather, but the velocity field and weak lensing show how heavy those gatherings truly are. The three together supply a consistent picture. Halos and filaments of dark matter stitch the sky into a network. Luminous systems hang from that network, and the flow follows the network's slopes rather than the brightness of any particular knot. The internal structure of halos complicates the very centers of clusters and galaxies, but matters little for the large-scale field when the data are smoothed to the appropriate scale. In a cluster-core galaxies orbit with high random speeds, and the hot gas is stirred by mergers and shocks. Those small-scale motions are averaged out when the aim is to recover the bulk drift across hundreds of millions of light years. What survives the averaging is the integrated pull of the halo and its environment. In a spiral galaxy, bars, spiral arms and feedback from young stars and black holes can rearrange gas and stars within a few tens of thousands of light years. Yet these processes do not erase the long, slow gradient imposed by the surrounding web. The discipline is to treat each scale with the tools it needs. Internal complexity is acknowledged and then set aside when reading the large-scale descent. Because dark matter does not shine, its distribution must often be inferred indirectly. Weak lensing supplies a light-independent map where feasible, by measuring the tiny coherent distortions imprinted on many faint background galaxies. X-ray observations of hot cluster gas interpreted with the physics of gases in deep wells provide mass profiles that agree in broad outline with lensing and with galaxy dynamics. Satellite motions around massive galaxies add further checks. These methods converge on a family of halo profiles that, when stacked across many systems, share common features regardless of whether the luminous content is rich or sparse. The consistency across techniques reduces the risk that a single window or a single tracer misleads the reconstruction of the field. On the larger scales, the statistical imprint of dark matter appears in the way galaxies cluster as a function of separation. A characteristic scale arises from sound waves that travelled through the hot, early plasma before light decoupled, leaving a faint preference for separations comparable to the distance such waves could cross. That preference is measured today as a weak bump in the correlation pattern of galaxies and as a matching wiggle in the power spectrum of density fluctuations. Its presence anchors the distance ladder at great depths and helps calibrate the expansion history. For the flow, it offers an external check when the reconstructed density field is turned into a forecast of how galaxies should cluster on large scales. The forecast should align with what is measured. Agreement does not reveal dark matter directly, but it strengthens the coherence of the picture in which dark matter sets the backbone that channels motion. Baryons, the ordinary matter in gas and stars, adjust to the dark framework and then feed back on small scales. Winds from young stars and growing black holes can push gas out of shallow halos, change star formation histories, and alter the way light traces mass locally. These processes seed dwarfs with variety that complicates any simple conversion from luminosity to mass. In a velocity-based map, this variety is a source of scatter rather than a fatal flaw. The peculiar velocities average over many systems and many lines of sight. They feel the combined weight of halos and filaments, regardless of whether those halos hold bright disks or are quenched by earlier feedback. In that sense, the flow is a democratic probe of the total matter field. The interpretation remains conservative about uncertainties. Distance errors propagate into peculiar velocities, and lensing measurements suffer noise where the sky is crowded or the background is sparse. The zone of avoidance reduces the usable background for shear measurements and obscures starlight that would otherwise show where halos host luminous systems. Analysts address these limits with smoothing that suppresses noise, while preserving coherent features with grouping that replaces the random orbits in crowded environments by bulk motions, and with cross-checks that test whether features survive changes in method sample and calibration. The hallmark of a real dark structure in the dynamical map is persistence. A ridge in lensing aligns with a bend in the flow. A string of hot clusters lies along the same direction. And the feature remains when catalogues are perturbed within their uncertainties. In the basin view, the role of dark matter is straightforward. It sets the contours. Voids owe their emptiness to a deficit of dark matter. Walls and filaments owe their gravity to an excess. Clusters mark the deepest blended wells where many halos coalesce. The local group sits in a modest halo threaded onto a filament whose slope is set by heavier structures nearby and by broad gradients from far fields. As a result, the peculiar velocity of the group is not an accident of starlight distribution. It is the expression of an invisible landscape in which ordinary matter is merely a painted edge. When streamlines arc toward the mid-scale convergence and then keep going, they do so because dark matter is arranged that way. When they cross the galactic plane without pause, they do so because the unseen envelope pays no attention to dust and foreground stars. The next inward step remains within the same frame but turns from what sculpts the field to how the present flow evolves over very long times. The basin's descent is shallow and extended. Bound islands retain their internal structures while the surrounding web continues its slow rearrangement. With dark matter's contours in mind, the forecast becomes a question of how currents that are gentle today change, as structures grow, and as the background expansion continues to accelerate. The method does not change. It keeps the universal rest frame fixed, treats motion as response to uneven weight, and follows the path inward from regional guidance toward the immediate neighborhood of the Milky Way, where the same principles apply with smaller amplitudes and longer patience. Forecasting the drift begins with the recognition that two influences act at once and on very long timescales. Gravity from uneven mass continues to gather matter into deeper structures, and the background expansion continues to accelerate under a property of space that acts like a uniform pressure. The first influence builds walls, filaments, and clusters from the seeds already present. The second influence stretches space faster and faster on the larger scales and reduces the ability of distant regions to communicate by gravity. The interplay sets the fate of the peculiar velocity field. Where matter is already bound, motion persists as orbits merges and slow relaxation. Where matter remains unbound, peculiar velocities gradually lose ground to the accelerating background, and the large-scale flow asymptotically freezes into a pattern that changes only slowly in moving coordinates. In this frame, the local group and its neighbors remain embedded in the basin already mapped by motion. The streamlines that cross our neighborhood today keep their shapes on large scales when viewed in an expanding grid. They continue to arc past the foreground wall, tighten near the obscured node, and aim toward the same interior. The pace of their inward drift slows in proportion to the changing balance between growth under gravity and the acceleration of the background. growth does not halt. It proceeds most where gradients are steepest near the nodes and along the thickest filaments. The acceleration trims the reach of further gathering by stretching the space between distant parts of the web. The result is a gradual segregation of scales. Bound islands evolve internally while the ocean between islands grows. Within the local group, the forecast is dominated by internal gravity. The Milky Way and Andromeda continue their approach along a nearly head-on line, and over several billions of years coalesce into a single more massive system. Their halos blend, their disks torque, and their stars rearrange into a new equilibrium. The bound companions of the pair either merge into the remnants, settle into long orbits, or are flung onto wider paths that remain inside the shared halo. These internal processes are not sensitive to the background expansion, because the group is already an island where gravity wins. The group's bulk translation through the basin continues, but its internal future is set chiefly by the enclosed mass rather than by the distant web. At intermediate distances, the forecast follows the slopes already measured. The cluster environment in Virgo continues to grow by accreting groups that approach along its feeding filaments. The wall in Hydra and Centaurus continues to collect matter from neighbouring voids, and its knots gain mass through mergers and infall. The obscured node near Norma remains an active participant in the same growth fed by streams that cross the galactic plane. These changes sharpen local contrasts without changing the gross orientation of the basin's flow. Streamlines that today skirt a void and aim along a filament will on the same comoving map follow the same corridor later, though the corridor thickens and the knots deepen. The peculiar velocity that carries the local group along that corridor remains as a gentle offset added to the background recession, rather than as a plunge toward a single sink. Farther out, the distant plateau of clusters that contributes a long-range component to the flow continues to gather mass from its surrounding filaments. The accelerating background, however, reduces the dynamical influence of such very distant regions on us with time. Signals propagate less effectively across ever larger stretches of space. The gradient that this plateau contributes to our neighbourhood today persists as a slow bias in direction, but its ability to alter speeds declines. In a comoving picture, the line of flow points the same way. In a physical picture, the incremental accelerations it adds weaken as the universe expands faster. A similar story holds for other far concentrations across the sky. Their presence today matters, yet their future pull becomes a fixed backdrop rather than a growing lever. The basin boundary responds to growth at its rim and to the slow stiffening effect of acceleration. Where saddles lie between adjacent domains, deepening of one side or the other can move a separatrix gently in comoving space. Such shifts are modest on human timescales. The map drawn today remains a good guide for very long periods because the rules that set it are conservative and because the features that would move its edges evolve slowly. Voids become emptier in a relative sense as walls and filaments continue to gather matter. Walls become more distinct. Clusters become more massive. The dynamical watershed that encircles the domain containing the Milky Way retains its integrity even as the interior rearranges. For forecasting simulations supply the most concrete guidance. When models start from early conditions that match the statistical imprint measured in the ancient microwave light and evolve forward under gravity and acceleration, they show a common pattern. Peculiar velocities on very large scales approach steady values in comoving coordinates. Bound structures merge along preferred directions. Filaments thicken and feed their nodes. Voids evacuate and expand relative to the mean. The approach towards steadiness is not a strict halt. Small residual changes continue as nearby masses grow. The point is qualitative. The large-scale currents that exist now do not reverse or scatter. They clarify as noisy small-scale motions die away, and they become easier to read even as the universe becomes more isolated from its farthest parts. A practical consequence concerns the reach of future influence. Objects that are not yet bound to a given cluster will find it increasingly difficult to become bound unless they already lie within a region where the cluster's gravity cancels the background expansion. That region is the turnaround shell. Its radius grows slowly as the cluster gains mass, but the accelerating background limits how far it can grow. For the cluster in Virgo, that shell remains well inside the distance to the local group for a very long time. The local group's motion includes a component toward Virgo, yet that component does not lead to capture. It remains a steady inward lean that never overwhelms the universal stretch across the full separation. The same logic applies to deeper structures. The mid-scale convergence and the distant plateau orient, and bias our path without enclosing it. The fate of light signals follows the same segregation. The accelerating background implies a cosmic event horizon, beyond which present emissions will never reach us. As time passes, more distant regions slide beyond that horizon. The structures that remain causally in touch with the local group shrink to a smaller, more local volume. Within that volume, dynamical interactions continue. Outside it, the web still evolves, but its changes no longer send news our way or receive our news in return. Forecasting the drift, then, is partly a forecast of fading connections. The nearby basin continues to shape our motion. Farther basins continue to evolve, but the influence they exert on us asymptotically settles. Within the local group's remnant, long after the merger of the two dominant spiral streams of stars and shells of debris, preserve memory of earlier passages. The merged halo continues to accrete smaller companions that fall along the same filamentary corridors. The coherent external field adds a slow shear to the outermost orbits, aligning some tidal features with the large-scale gradient. These imprints are subtle and take many billions of years to write, yet they are a record of the same flow that guides the group today. They show that even when a system becomes a single island, its edges still remember the continental slope beneath the sea. In the statistical sense, consensus holds that the acceleration of the background continues, and that large-scale growth slows without stopping completely in the places already most dense. The lesser-known detail is that the approach to a frozen flow happens first on the larger scales, and only later on intermediate scales, so that near nodes the field keeps changing longer than it does across wide voids and shallow shelves. The remaining uncertainty is how precisely the basin boundaries shift in response to the detailed growth of mass near saddles, given that distance errors, selection effects and masked sky sectors still limit reconstruction at the finest allowed smoothing. The planetary scale observation is that within a few tens of millions of light-years the motions of many groups remain coherently aligned with the same downstream direction, and that this alignment persists in forecasts as a defining feature of our neighbourhood. The forecast does not assign meaning beyond mechanics. It says that motion responds to weight and that weight is arranged in a web dominated by dark matter. It says that acceleration makes far horizons recede and turns present flows into nearly steady currents when seen on a grid that expands with space. It says that the Milky Way's path is a composite of nearby nudges and distant slopes that add to a single modest vector carried across many scales. With these points established, the narrative can take its final inward step and end at the immediate environment, where this same composite vector is felt as a quiet drift through the solar neighbourhood, completing the path from the outer map to home without breaking the frame or the rules that have held from the beginning. In the immediate neighbourhood of the Milky Way, the great currents that cross supercluster basins are felt as a quiet offset within a landscape of gas dust and stars. The galaxy is a barred spiral set inside a dark halo. Its thin disk carries lanes of cold gas and bright nurseries. Its thick disk holds older populations whose motions rise above the plane, and its stellar halo drapes outward with streams that remember earlier mergers. None of these components notices the expansion of space inside the galaxy. Bound islands keep their own time. What they do register is a small, steady drift that adds to internal orbits the local expression of the wider field that has guided this narrative inward. In this frame, the Sun moves on a nearly circular path within the disk, tilted slightly with respect to the midplane and traced with small epicyclic wiggles that reflect the galaxy's potential. Superposed on that orbit is the bulk translation of the Milky Way and its companions through the basin's gentle gradient. The local standard of rest built by averaging the motions of stars near the Sun provides a practical reference for separating the solar orbit from the broader drift. When the motions of many nearby stars are gathered and expressed in the rest frame of the ancient microwave light, the residual field across the solar neighbourhood points toward the same hemisphere that earlier sections identified as dynamically downhill. No single star demonstrates this fact. The field appears only when many small arrows are read together. The immediate extragalactic setting is a flattened assembly of nearby galaxies that move more coherently than the wider field. This structure, often called the local sheet, defines a plane across which peculiar velocities are relatively small and perpendicular components carry most of the change. The sheet places the Milky Way and its neighbours alongside a broad, underdense region, sometimes called the local void. The presence of that void matters. Where mass is low motion points outward. The outward tendency from the void side reduces counterpulls and leaves a net lean that helps align nearby groups toward the same broad longitudes. In maps smoothed on suitable scales, the local sheet looks like a raft sliding along a mild slope with one edge lifted by emptiness and the other pressed by surrounding structure. Closer still, the Sun dwells in a cavity of hot, thin gas called the local bubble, bordered by denser clouds and shells carved by past winds and supernovae. The bubble spans a few hundred light years and hosts chains of young stars along its rim. These features shape radio and X-ray foregrounds and complicate methods that rely on dust absorption, yet they do not alter the galaxy's bulk motion. They are weather in one district of a larger island. Their value here is calibration. The geometry explains small differences among distance indicators inside the neighbourhood, and clarifies why certain sightlines differ in extinction and crowding without implying any change to the direction of the wider flow. The streams in the Milky Way's halo carry a longer memory. They are the debris of small galaxies and clusters pulled apart by tides and wrapped around the galaxy on elongated paths. Each stream records the shape of the dark halo and hints at the history of infall along the filament that feeds the local group. Over many billions of years, these streams lengthen and fade, but their orientations continue in the statistical sense, to align with the large-scale gradient that threads the basin. In this way, the outer halo preserves both the local past and the slow shear imposed by the surrounding web. The galaxy's companions add further context. Dwarf satellites move on elongated orbits that trace the outer halo and register recent accretion. Some define thin planes for a time, though over long spans those planes disperse as orbits precess in the halo's potential. The brightest satellites trail gas and stars that arc across the sky and record both internal tides and the slow guidance of the external field. Averaged over many systems, their apocenters and pericenters echo the larger descent, not because a single beacon commands them, but because the combined gravity of halos and filaments leans their paths the same way. Stellar surveys sharpen the local picture by measuring motions with great precision. Parallax fixes distances to individual stars, proper motions track tiny drifts across the sky, and radial velocities record motion along the line of sight. Combined, these data reveal ripples in the disk from past encounters, bending waves in the outer gas layer, and subtle asymmetries in the distributions of young and old stars. These features complicate immediate kinematics, but average away when the map is smoothed to the scales appropriate for bulk motion. The discipline that governed earlier sections still holds. Keep the frame fixed group objects that share a halo and let coherent features outweigh local noise. A small set of statements frames what is most secure, what is less familiar, what remains unresolved, and what spans a planetary scale. The factual consensus point is that the Milky Way and Andromeda are bound and approach along a nearly head-on line, while the local group as a whole carries a modest, peculiar velocity aligned with the regional convergence already mapped. The lesser-known detail is the dynamical distinctness of the local sheet, whose small internal scatter and sharp contrast with the adjacent void focus nearby flow more tightly than a simple count of luminous neighbours would suggest. The unresolved mystery is the precise shape and orientation of the Milky Way's dark halo on the largest radii now traced by faint streams, a property that controls how long satellite planes persist and how rapidly streams precess. The planetary scale observation is quiet and continuous. The solar system with its planets and belts and clouds rides inside this larger drift without noticing it, while the same drift threads through the volumes that modern surveys measure star by star. The Sun's path carries it slowly in and out of the midplane and around the centre, while the galaxy as a whole slides through the basin. Over spans far longer than human lives, the relative angle between the solar orbit and the basin's drift can change how streams and satellite structures are viewed from the Earth, yet it does not change the fact of the drift. The solar neighbourhood therefore experiences the large-scale field as an almost constant breeze too light to feel in the orbits of planets and too gentle to disturb the internal order of the disk, but strong enough when read statistically to place our home inside a wider current. The method that made the larger map remains the way to see this breeze. The frame is the rest frame of the microwave background. The expansion is subtracted to reveal peculiar velocities. Distances are the gatekeepers between noise and signal. Grouping and smoothing keep local complexity from masquerading as bulk motion. Within this discipline, the Milky Way is one island inside a watershed called Laniakea. Its neighbours in the local sheet slide with it. The nearby cluster environment adds a modest inward component. The mid-scale foreground reorients paths across a wide span of longitudes. The obscured node behind the plane deepens the same descent. The far plateau of clusters adds a long-range bias that continues beyond. The sum is the single patient vector that threads the galaxy's neighbourhood today. The path that began at the universal background ends at home without changing the rules. The expansion sets the rhythm. Dark matter sets the contours. Gravity guides motion down gentle slopes, and light marks only the crests of a deeper landscape. The Milky Way, with the Sun and its planets embedded in one quiet arm of its disk, moves through that landscape with steady grace. The drift does not announce itself in a single image. It appears when many measurements are gathered and read together as a field. Once seen, it gives a final simple placement. The galaxy is a bound island carried along inside a basin, whose boundaries are drawn by motion. The currents cross the plane, ignore dust and foreground stars, arc past nearby weights, and continue toward a shared interior that lies well beyond any single luminous knot. The map is complete enough to steer by, and cautious enough to endure. It finishes at the solar neighbourhood because that is the natural end of an outer to inner route, not because the currents cease. They continue steady and slow beneath the familiar sky.